Imagine spending your entire career piecing together a puzzle. Now imagine that 99% of the pieces are missing. The few pieces you do have are broken, warped by time, crushed under millions of years of rock and sediment. Some of them don't even look like they belong to the same puzzle. And yet you are expected to look at those fragments and tell the world exactly what the completed picture looks like. That is paleontology. That is the impossible, magnificent, deeply humbling science of reading the history of life on Earth from nothing more than bones, impressions, and traces left behind in stone. It is a science built on inference. It is a science built on educated guessing. And because of that, it is a science where mistakes are not just possible, they are inevitable. The fossil record is not a library. It is not an archive neatly organized for our convenience. It is a graveyard, and like all graveyards, it keeps its secrets buried. For every animal that ever lived on this planet, the overwhelming majority left behind no trace at all. Their bodies decomposed, their bones scattered, their very existence erased as if they had never drawn breath. The creatures we do find preserved in rock represent a tiny, almost laughably small fraction of the life that has existed over the past 3.5 billion years. And even when we find them, the fossils themselves are often incomplete, distorted, or so alien in appearance that the scientists who first encounter them have no frame of reference for understanding what they are looking at. This is a story about those moments of confusion. This is a story about the times when some of the greatest minds in the history of science looked at the evidence in front of them and got it spectacularly, sometimes hilariously, sometimes understandably wrong. These are not stories of incompetence. These are stories of brilliant people doing the best they could with the information available to them, working in an era before the tools and knowledge we take for granted today existed. Their mistakes were not failures. They were stepping stones. Every wrong turn, every misidentification, every bizarre and outlandish reconstruction that later turned out to be wildly inaccurate pushed the science forward, forced researchers to ask better questions, develop better methods, and look at the natural world with sharper, more critical eyes. Because here is the truth that every honest paleontologist will tell you, the history of their field is littered with errors. Dinosaurs that turned out to be fish. Spiders that turned out to be sea scorpions. Turtles that turned out to be dinosaurs. Swimming creatures that turned out to fly. Single animals that were split into 3 entirely different organisms. And perhaps most humbling of all, animals that science declared extinct for 66 million years that turned out to be swimming in the ocean the entire time, waiting to be noticed. These are the greatest mistakes in the history of paleontology. And every single one of them is fascinating. Let us begin at the very beginning, or at least as close to the beginning as the science of paleontology gets. Because to understand how mistakes happen, you first have to understand the world in which those mistakes were made. And to understand that world, you have to go back to a time before the word dinosaur even existed. The early 19th century was a period of extraordinary intellectual ferment. Across Europe, the sciences were exploding with new discoveries and new ideas. Geology was emerging as a formal discipline, and with it came a growing awareness that the Earth was far, far older than anyone had previously imagined. The rocks beneath people's feet were not simply inert matter. They were pages in a book, layers of history stacked one on top of another, each one representing a different chapter in the planet's past. And embedded within those layers were objects that defied easy explanation: bones, teeth, shells, and impressions of creatures that bore no resemblance to anything alive in the modern world. People had been finding these objects for centuries, of course. Ancient civilizations had stumbled upon fossils and woven them into their myths and legends. Giant bones became the remains of heroes and titans. Massive teeth were attributed to dragons. Petrified shells found high in the mountains were taken as evidence of a great flood. But in the early 1800s, a new generation of thinkers was beginning to approach these objects with the tools of reason and observation rather than mythology. They were beginning to ask a dangerous and thrilling question: what if these are the remains of real animals? Animals that once lived and breathed and walked the earth, but which no longer exist? This was a radical idea. The concept of extinction was still controversial. Many theologians and philosophers argued that a perfect God would not create an animal only to allow it to die out. Every species that had ever existed, they insisted, must still exist somewhere in the world, perhaps in some unexplored corner of a distant continent, or in the unfathomed depths of the ocean. But the evidence was becoming harder and harder to deny. The bones being pulled from the quarries and cliffs of England and France were simply too large, too strange, too fundamentally different from any living animal to be explained away. Something enormous and unknown had once lived in these places. And whatever it was gone. It was into this charged atmosphere of discovery and debate that one of the most important and most misunderstood animals in the history of paleontology made its entrance. The story of Megalosaurus begins not in a laboratory or a museum, but in a limestone quarry in Oxfordshire, England. The exact date of the first discovery is lost to history, but we know that large bones had been turning up in the Stonesfield slate quarries since at least the late 17th century. In 1676, a partial femur was described by Robert Plot, the first keeper of the Ashmolean Museum at Oxford. Plot recognized that the bone was too large to belong to any living animal in England. He initially speculated that it might be the thigh bone of a giant human, a relic of a race of biblical giants, but he could not be certain. The bone was illustrated, described, and then largely forgotten. Over the next century and a half, more bones emerged from the quarries. Jaw fragments studded with massive, curved, serrated teeth. Vertebrae as big as a man's fist. Limb bones thick and heavy, suggesting an animal of tremendous size. These fragments accumulated in private collections and university cabinets, curiosities without context, pieces of a puzzle that no one yet knew how to assemble. The man who would finally attempt to make sense of these fragments was William Buckland, a professor of geology at Oxford and one of the most colorful characters in the history of science. Buckland was brilliant, eccentric, and inexhaustible. He was famous for his wild lectures, his habit of keeping hyenas and other exotic animals in his home, and his professed ambition to eat his way through the entire animal kingdom. He was also one of the first people to recognize that the bones from Stonesfield represented something genuinely new and extraordinary. By the early 1820s, Buckland had assembled a collection of fossils from Stonesfield that, while far from complete, was enough to attempt a description. He had a partial lower jaw with teeth, several vertebrae, fragments of the pelvis, and portions of the hind limb. It was not much to work with, but Buckland was not a man who shied away from a challenge. In 1824, Buckland presented his findings to the Geological Society of London. He named the animal Megalosaurus, meaning great lizard. It was among the very first dinosaurs ever to receive a formal scientific name. This was a moment of genuine scientific triumph. Buckland had correctly identified the remains as belonging to a large, carnivorous reptile. His description of the teeth was masterful, noting their serrated edges and their resemblance to the teeth of modern monitor lizards, only vastly larger. He recognized that the animal was a predator, and that it was of a size that dwarfed anything alive in the modern world. But here is where the problems began. Because while Buckland got many things right, the overall picture he painted of Megalosaurus was fundamentally, almost comically wrong. Buckland, working with the limited comparative anatomy available to him, imagined Megalosaurus as essentially an enormous lizard. Not a lizard in the loose, colloquial sense that we sometimes apply to dinosaurs, but an actual lizard, a sprawling, belly-dragging, four-legged reptile, scaled up to monstrous proportions. He envisioned it as a creature that walked on all fours, its legs splayed out to the sides in the manner of a modern crocodile or iguana. Its body would have been long and low-slung, its tail dragging behind it like a great, scaly rope. To our modern eyes, this reconstruction is almost unrecognizable. Megalosaurus, as we understand it today, was a bipedal theropod dinosaur, a two-legged predator that stood upright, balanced on its powerful hind limbs, with its tail held stiffly behind it as a counterweight. It would have been an active, agile hunter, nothing at all like the ponderous, swamp-dwelling lizard that Buckland imagined. The difference between the real Megalosaurus and Buckland's version is roughly equivalent to the difference between a tiger and an alligator. They are both reptilian predators, broadly speaking, But in every aspect of their anatomy, behavior, and lifestyle, they are utterly different animals. But we must be fair to Buckland. We must resist the temptation to mock him from the comfortable vantage point of 200 years of accumulated knowledge. Because in 1824 there was no concept of a bipedal reptile. The very idea would have seemed absurd. Every large reptile known to science walked on 4 legs. The notion that there had once existed an entire group of reptiles that stood upright like birds was simply outside the realm of what anyone considered possible. Buckland was working from analogy, and the best analogy available to him was the modern lizard. So a lizard is what he gave the world. An enormous, terrifying, magnificent lizard. Wrong in almost every particular, but groundbreaking nonetheless. The Megalosaurus story did not end with Buckland, of course. In fact, it was about to get both better and worse. Because within a few years of Buckland's description, other scientists began to grapple with the same questions, and their answers were not much closer to the truth. Enter Richard Owen. If William Buckland was the enthusiastic amateur who stumbled into greatness, Richard Owen was the consummate professional who seized it with both hands. Owen was a comparative anatomist of extraordinary skill, a man whose knowledge of animal skeletons was perhaps unmatched in his generation. He was also, by most accounts, an intensely difficult person, ambitious, combative, and not above taking credit for the ideas of others. But whatever his personal failings, his scientific contributions were immense. In 1842, Owen did something that would change the way humanity understood its planet. He looked at the scattered descriptions of Megalosaurus, Iguanodon, and Hylaeosaurus, 3 large, extinct reptiles that had been described in the preceding decades, and recognized that they shared certain anatomical features that set them apart from all other known reptiles. They were not simply oversized lizards or crocodiles. They were something else entirely, something that required a new category. Owen coined the term Dinosauria, meaning terrible lizards, or, more accurately, fearfully great lizards. With that single word, he created an entirely new concept in the public imagination, the dinosaur. Owen's recognition that dinosaurs were distinct from modern reptiles was a major step forward. But his reconstruction of what they actually looked like was still profoundly wrong, just wrong in new and different ways. Owen imagined dinosaurs as massive, elephant-like quadrupeds. Not the sprawling lizards of Buckland's vision, but upright, column-legged behemoths, more rhinoceros than iguana. His Megalosaurus stood on 4 thick, pillar-like legs, its body held high off the ground, its posture more mammalian than reptilian. This vision reached its most famous expression in the Crystal Palace Dinosaurs, a series of life-size sculptures created by the artist Benjamin Waterhouse Hawkins under Owen's direction in 1854. These sculptures, which still stand in a park in South London, depict Megalosaurus and its contemporaries as ponderous, heavy-bodied creatures, more akin to oversized hippos than to the lean, agile predators we now know them to have been. The Crystal Palace Megalosaurus is a quadruped. It has a pronounced hump over its shoulders. Its head is positioned low, like a bulldog's. It looks, frankly, ridiculous by modern standards. And yet millions of people saw those sculptures and accepted them as accurate representations of prehistoric life. For decades, the Crystal Palace dinosaurs shaped the public's understanding of what these animals looked like. They were reproduced in books, illustrated in magazines, and referenced in scientific papers. The image of Megalosaurus as a lumbering, 4-legged beast became entrenched in the popular imagination and proved remarkably difficult to dislodge. It was not until the late 19th and early 20th centuries that the true nature of theropod dinosaurs began to come into focus. The discovery of more complete skeletons, including those of related theropods in other parts of the world, gradually made it clear that animals like Megalosaurus were not quadrupeds at all. They walked on 2 legs. Their forelimbs were small and grasping, not weight-bearing. Their tails were not dragged along the ground but held aloft, serving as dynamic counterbalances. Their skulls were positioned high on flexible necks, giving them a field of vision more like that of an eagle than a crocodile. The transformation of Megalosaurus from a crawling lizard monster to a striding, bipedal predator was one of the most dramatic revisions in the history of paleontology. It was not a single moment of revelation but a slow, painstaking process that played out over more than a century, driven by the accumulation of new fossils, new analytical techniques, and new ways of thinking about the relationships between extinct and living animals. But the story of Megalosaurus also illustrates a deeper truth about paleontology that applies to every case we will examine. The fossil record is a trickster. It gives you just enough information to form a hypothesis, but rarely enough to confirm it beyond doubt. Buckland had a jaw, some teeth, a few vertebrae, and fragments of limb bones. From those scraps, he was expected to reconstruct an entire animal, its posture, its gait, its lifestyle, its place in the ecosystem. It is a testament to his skill that he got as much right as he did. It is a testament to the difficulty of the task that he got so much wrong. And Megalosaurus, despite being among the first dinosaurs ever named, remains one of the most poorly understood. Even today, 200 years after Buckland's original description, the animal is known from frustratingly incomplete remains. We have a much better understanding of its general anatomy thanks to the discovery of closely related species. But the original Megalosaurus bucklandi, the type species, is still something of a mystery. Its exact size, its precise appearance, the details of its behavior, all of these remain subjects of debate. The great lizard that started it all continues to guard its secrets. Let this be our first lesson, then. Paleontology is a science of humility. Even when you are making history, even when you are naming the very first dinosaur, you can still get it wrong. And that is not a weakness of the science. It is its fundamental nature. Now let us leave the familiar territory of dinosaurs behind for a moment, and venture into a different world, a world that is, in many ways, even more alien and even more prone to misinterpretation. We are going to talk about arthropods. Specifically, we are going to talk about one of the most embarrassing misidentifications in the history of invertebrate paleontology. We are going to talk about Megarachne. Before we get to the animal itself, let us set the stage. The Carboniferous period, which lasted from roughly 359 million years ago to 299 million years ago, was a time of extraordinary biological productivity. Vast, swampy forests covered much of the Earth's land masses. The atmosphere was rich in oxygen, significantly richer than it is today, and this surplus of oxygen allowed arthropods to grow to sizes that would seem nightmarish by modern standards. Dragonflies with wingspans of over 2 feet patrolled the skies. Millipedes the length of a car crawled through the undergrowth. Scorpions as long as a man's arm hunted in the leaf litter. It was, by any measure, the age of the giant bug. In this context, the discovery of what appeared to be a giant spider was not entirely surprising. If dragonflies could grow to the size of hawks and millipedes could reach the length of crocodiles, why not a spider of monstrous proportions? The idea was terrifying but biologically plausible. Or so it seemed. The fossil that would become Megarachne was discovered in the San Luis province of Argentina, in rocks dating to the late Carboniferous, approximately 300 million years ago. The specimen was found by an amateur collector and eventually came to the attention of the Argentine paleontologist Mario Huniken. In 1980, Huniken described the fossil in a scientific paper that would ignite imaginations around the world. He named it Megarachne cervinii, the great spider, and described it as the largest spider ever known, with a body length estimated at over 13 inches and a leg span that, by extrapolation, would have been truly horrifying. The paper was a sensation. The idea of a spider the size of a dinner plate, prowling the Carboniferous forests of ancient South America, captured the public imagination in a way that few paleontological discoveries do. Megarachne appeared in books, documentaries, and museum exhibits. It became the poster child for the Carboniferous gigantism phenomenon, proof that the age of the giant bugs had produced horrors beyond imagining. There was just one problem. Megarachne was not a spider. To understand why this mistake was made and how it was eventually corrected, we need to talk about what the fossil actually looked like and why it was so confusing. The original specimen was preserved as a series of impressions in rock, basically, a flattened, two-dimensional imprint of the animal's body. The preservation was not ideal. Many details were obscured, smudged, or missing. But certain features seemed, at first glance, to align with what you would expect from a spider. There appeared to be a divided body plan, with a front section, the cephalothorax or prosoma, and a rear section, the opistosoma. There seemed to be evidence of large, fawn-like structures at the front. The overall shape and proportions were broadly consistent with a spider, if you squinted hard enough and wanted badly enough for it to be one. And that, ultimately, is what went wrong. There is a phenomenon in science known as confirmation bias, the tendency to interpret evidence in a way that supports what you already believe or what you want to be true. Huniken approached the fossil with the hypothesis that it was a spider, and he interpreted the ambiguous features accordingly. The fawn-like structures became chelicerae. The body divisions became the familiar two-part body plan of an arachnid. The overall size was breathtaking but not impossible, given what was already known about Carboniferous gigantism. Everything seemed to fit. But other scientists were not so sure. Over the years following Huniken's original description, several researchers expressed skepticism about the spider identification. The fossil was not clearly preserved enough to be confident in many of the key features that Huniken had described. Some of the supposed spider characteristics were ambiguous at best. And there were nagging inconsistencies, aspects of the fossil that did not quite match what you would expect from any known group of spiders, living or extinct. The problem was that the original specimen was the only one known, and it was held in a collection in Argentina that was not easily accessible to other researchers. For years, the debate simmered without resolution. Some scientists accepted Megarachne as a spider. Others rejected it. Most simply noted the uncertainty and moved on. Then, in 2005, everything changed. A team of researchers led by Jason Dunlop of the Humboldt Museum in Berlin obtained access to the original specimen and, crucially, to additional fossil material that had been collected from the same locality. With fresh eyes, better tools, and more material to work with, they re-examined the evidence. And their conclusions were devastating. Megarachne was not a spider at all. It was a eurypterid, a sea scorpion. Eurypterids are an extinct group of aquatic arthropods that thrived during the Paleozoic era. Some of them were indeed enormous, with the largest species reaching lengths of over 8 feet. They are among the most impressive arthropods ever to have lived. But they are not spiders. They are not even closely related to spiders, in the grand scheme of arthropod phylogeny. They are chelicerates, yes, which means they share a common ancestor with arachnids, but the evolutionary split between eurypterids and true spiders happened hundreds of millions of years ago. Calling Megarachne a spider because it is a chelicerate is like calling a whale a rodent because both are mammals. The features that Huniken had interpreted as spider characteristics turned out to be typical eurypterid features when viewed without the bias of a preconceived identification. The supposed chelicerae were not chelicerae at all but were structures consistent with the appendages of a eurypterid. The body divisions were not the prosoma and opistosoma of a spider but the prosoma and opistosoma of a sea scorpion, which, while superficially similar in basic layout, differ in many crucial details. The overall proportions, once freed from the spider template, were a much better fit for a eurypterid. Dunlop and his colleagues were meticulous in their redescription. They went through the fossil feature by feature, comparing each one against both spider and eurypterid anatomy, and in every case, the eurypterid interpretation was more parsimonious, more consistent, and more convincing. Megarachne cervinii was reclassified as a eurypterid, specifically as a member of the family Micteropodidae. The world's largest spider vanished overnight, replaced by a large but not particularly remarkable sea scorpion. The reclassification was widely accepted by the scientific community, but its effects on popular culture took longer to filter through. For years after the correction, Megarachne continued to appear in books, websites, and documentaries as a giant spider. Some of these references were simply outdated, materials produced before the reclassification that were never updated. But others reflected a deeper problem. The world wanted Megarachne to be a spider. The idea of a giant spider was too compelling, too viscerally thrilling, to be easily abandoned. A giant sea scorpion, while impressive, simply did not have the same emotional impact. This is a pattern we will see again and again in the stories that follow. When a fossil discovery captures the public imagination, the original interpretation tends to stick, even after it has been corrected. The first story told about a fossil is almost always the one that people remember, regardless of whether it turns out to be true. This is not a failing of the public. It is a reflection of how human memory and narrative work. We remember stories. We forget corrections. And in paleontology, the first story is often the most dramatic one, because the first story is the one told with the least information and the most imagination. But let us return to Megarachne for a moment longer, because there are deeper lessons to be drawn from this case. First, there is the question of access. Huniken's original description went largely unchallenged for 25 years, in part because other researchers could not easily examine the fossil firsthand. In an ideal scientific world, every significant specimen would be readily accessible to any qualified researcher who wanted to study it. In reality, fossils are physical objects housed in specific institutions, and access can be limited by geography, politics, institutional policies, and simple logistics. When a fossil can only be studied by a handful of people, the chances of an error going undetected increase dramatically. The Megarachne case is a powerful argument for open access in paleontology, for the idea that important specimens should be available for study, whether through physical loans, high-resolution casts, or, increasingly, digital scans. Second, there is the question of expertise. Huniken was a vertebrate paleontologist, not a specialist in arachnid or eurypterid anatomy. This is not a criticism. Paleontology is a vast field, and no one can be an expert in everything. But it does highlight the importance of interdisciplinary collaboration. When a fossil falls outside your area of specialization, the prudent thing to do is to consult with someone who knows the relevant anatomy inside and out. Huniken's mistake might have been caught much sooner if the original description had involved a specialist in chelicerae morphology. Third, and perhaps most importantly, there is the question of how we deal with ambiguity. The Megarachne fossil was ambiguous. It was poorly preserved. Many of its features could be interpreted in multiple ways. Huniken chose to interpret those features in the way that produced the most exciting result, a giant spider. The temptation to do this is enormous, and not just in paleontology. In every field of science, there is a pull toward the dramatic, the groundbreaking, the publishable. Ambiguous data is like a Rorschach test. You can often find in it whatever you are looking for. The best scientists are the ones who can resist this pull, who can look at ambiguous evidence and say, honestly and without embarrassment, I don't know what this is. That is a hard thing to do. It does not make for exciting press releases. It does not generate headlines. But it is, in the long run, the only honest response to uncertainty. And in paleontology, uncertainty is the only constant. Megarachne is not the largest spider that ever lived. The largest spider that ever lived is probably alive today, the Goliath bird-eater tarantula of South America, with a leg span of up to 12 inches. That may seem disappointing compared to the nightmare vision of Megarachne, but there is a lesson in that disappointment too. Nature does not need to conform to our fantasies. The real world is strange enough without our embellishments. And sometimes the truth, a large but otherwise unremarkable sea scorpion, is more interesting than the fiction, if only because it reminds us of how easily we can deceive ourselves. Now we turn to a case that is, in many ways, even more bizarre than Megarachne. We are going to talk about an animal whose fossils were so confusing, so utterly alien to anything in the experience of the scientists who found them, that the creature was mistaken for a turtle. A giant, swimming, seaweed-eating turtle, with claws the length of swords. We are going to talk about Dinosaurs. The story begins in the Gobi Desert of Mongolia, one of the richest and most important fossil localities on Earth. The Gobi has been yielding extraordinary discoveries since the 1920s, when a series of expeditions launched from the west first explored its vast, arid expanses. It was in the Gobi that the first confirmed dinosaur eggs were found. It was in the Gobi that Velociraptor was discovered, locked in combat with Protoceratops in one of the most famous fossils ever unearthed. And it was in the Gobi, in 1948, that a Soviet-Mongolian paleontological expedition stumbled upon something that would confound the scientific world for decades. The expedition, led by a team of Soviet and Mongolian scientists, was exploring late Cretaceous sediments in the Nemegt Formation when they uncovered a set of enormous claws. Not just large claws, enormous ones. Each individual claw was roughly 2.5 feet long, gently curved, and flattened from side to side. They were, without exaggeration, among the largest claws ever discovered on any animal, living or extinct. Alongside the claws were fragments of the forelimbs, including portions of the arm bones and some rib fragments. But that was it. No skull. No legs. No vertebrae. No pelvis. Just those massive, inexplicable claws and the arms that bore them. The Soviet paleontologist Yevgeny Maleev described the fossils in 1954. He named the animal Therizinosaurus kilaniformis, a name that tells us a great deal about his interpretation. Therizinosaurus means reaping lizard, or scythe lizard, a reference to the enormous, blade-like claws. But it is the species name, kilaniformis, that is most revealing. Kilaniformis means turtle-shaped. Maleev believed, and he had reasons for this belief, as we shall see, that Therizinosaurus was some kind of giant turtle. Now, to be clear, this was not a casual or lazy identification. Maleev was a respected paleontologist who had described numerous dinosaur species from the Gobi. His turtle hypothesis was based on a careful, if ultimately misguided, analysis of the available evidence. The flattened shape of the claws, their gentle curvature, and the overall robustness of the arm bones reminded him of the flippers and claws of certain large sea turtles. The rib fragments, which were broad and flat, also seemed consistent with a turtle-like body plan. And the sheer size of the claws suggested an aquatic animal, since large claws of that type would be impractical on land. Or so Maleev reasoned. His vision of Therizinosaurus was extraordinary. He imagined a turtle of staggering proportions, far larger than any turtle known to science, living or extinct. This giant turtle would have inhabited the shallow seas and waterways of the late Cretaceous Gobi, using its massive claws to rake through beds of underwater vegetation, harvesting seaweed and aquatic plants. The claws, in this interpretation, were not weapons but feeding tools, biological scythes for gathering food. It is a vivid and imaginative reconstruction. It is also completely, utterly, magnificently wrong. To understand why Maleev went astray, we need to consider the context. In the early 1950s, the concept of theropod diversity was still relatively limited. The theropod dinosaurs known at that time were mostly carnivorous, with relatively small forelimbs and claws that, while sometimes large, were clearly adapted for grasping prey. No one had yet imagined a theropod with claws this large, because no theropod known at the time had claws even remotely approaching this size. The claws of Therizinosaurus were so far outside the expected range for any dinosaur that they seemed to belong to an entirely different kind of animal. Furthermore, the Nemegt Formation, where the fossils were found, was known to contain a mix of terrestrial and aquatic environments. The presence of large, aquatic animals in these sediments was not unexpected. And in the absence of clear dinosaurian features, no distinctive dinosaur skull, no obviously dinosaurian vertebrae, no bipedal leg bones, there was nothing in the available material that screamed dinosaur to a researcher in the 1950s. The turtle hypothesis, while wrong, was a reasonable response to a deeply confusing set of fossils. But the story did not end there. Over the following decades, more fossils were found in the Gobi and in neighboring regions of China that gradually chipped away at the turtle hypothesis and replaced it with something far stranger. In the 1970s, the Mongolian paleontologist Rinchen Barsbold described a series of new dinosaur genera from the Nemegt Formation that shared some features with Therizinosaurus. These animals, which included species like Segnosaurus and Erlikosaurus, were clearly dinosaurs. They had dinosaurian vertebrae, dinosaurian pelvis, and other features that left no doubt about their classification. But they were strange dinosaurs. They had small heads, long necks, broad bodies, and, crucially, large, clawed hands. They did not look like typical theropods. They did not look like typical anything. Barsbold placed them in their own group, the Segnosauria, and proposed that they might be related to sauropods or even ornithischian dinosaurs rather than to theropods. This was itself a mistake, but a productive one. By recognizing that these animals formed a distinct group, Barsbold laid the groundwork for the eventual correct identification of Therizinosaurus. As more material was found and studied, it became increasingly clear that the Segnosauria, later renamed Therizinosauria, were indeed theropod dinosaurs, but theropods of a kind that no one had previously imagined. They were herbivorous theropods. Or at least partially herbivorous. Their small heads and leaf-shaped teeth were adapted for eating plants, not meat. Their broad bodies housed the large guts necessary for digesting plant matter. Their massive claws, far from being aquatic feeding tools, may have been used for defense against predators, for pulling down branches to feed, or for some combination of both purposes. Therizinosaurus itself, the animal with the largest claws of all, was gradually recognized as the most extreme member of this group. Its claws, once thought to be the flippers of a giant turtle, were now understood as the exaggerated weapons or tools of a bizarre, pot-bellied, feathered dinosaur that lumbered through the forests of the late Cretaceous Gobi. It was not a swimmer. It was not a turtle. It was a dinosaur, but a dinosaur unlike anything that Maliv or his contemporaries could have imagined. The full picture of Therizinosaurus took decades to assemble, and required the discovery of numerous related species, each one providing a few more pieces of the puzzle. It was not until the late 1970s and early 1980s that the theropod identity of the group was firmly established, and even then, debates about the precise relationships within the group continued for years. Some researchers argued that therizinosaurs were not theropods at all but belonged to some other lineage of dinosaurs. Others accepted the theropod classification but disagreed about which other theropods were their closest relatives. These debates were healthy and productive, driving new research and new discoveries. But they also illustrated the fundamental difficulty of working with incomplete fossils. Consider the challenge that Maliv faced. He had enormous claws and fragments of arms. Nothing else. From those pieces, he was asked to reconstruct an entire animal. He knew it was big. He knew it had impressive claws. He knew it came from sediments that included aquatic environments. What would you have concluded? In the absence of any framework for understanding what a herbivorous theropod might look like, because no one had yet imagined such a thing, the turtle hypothesis was arguably as good as any. It was wrong, but it was not unreasonable. And this brings us to a broader point about how science works. Science does not progress by getting everything right the first time. It progresses by getting things wrong, recognizing the errors, and then getting things a little less wrong the next time. Maliv's turtle was wrong. Barsbold's Segnosaur was less wrong. The modern understanding of Therizinosaurus as a herbivorous theropod is, we believe, substantially right. But who knows what future discoveries might reveal? Perhaps in another 50 years, our current reconstruction will seem as quaint and misguided as Maliv's turtle. The history of Therizinosaurus is a history of science doing what science does, stumbling forward through a fog of uncertainty, occasionally tripping, occasionally falling flat on its face, but always getting back up and taking another step. Let us now take a step in a different direction entirely. Let us leave the ground behind and take to the air. Because the next animal on our list is one that was so strange, so unlike anything that had come before, that the scientists who first encountered it could not even agree on what kind of animal it was, let alone what it looked like. We are going to talk about Pterodactylus. And to understand why this animal caused so much confusion, we need to go back even further than Buckland and Megalosaurus, back to the very dawn of paleontological thought. The fossil that would eventually be named Pterodactylus antiquus was discovered in the Solnhofen limestone of Bavaria, Germany, sometime in the late 18th century. The Solnhofen limestone is one of the most remarkable geological formations in the world. It consists of extremely fine-grained limestone that was deposited in a tropical lagoon during the late Jurassic period, approximately 150 million years ago. The conditions in that lagoon were extraordinary. The water was warm, shallow, stagnant, and nearly devoid of oxygen. Animals that fell into the lagoon, or were swept into it by storms, sank to the bottom and were rapidly buried in the fine sediment, preserving them in astonishing detail. The Solnhofen limestone has yielded some of the most beautifully preserved fossils ever found, including delicate insects, fish with every scale intact, and most famously, the feathered dinosaur Archaeopteryx. It was from these same exquisite limestones that the first pterodactylus emerged. And it was, by any measure, one of the strangest animals that anyone in the 18th century had ever seen. The specimen was essentially complete, a rare luxury in paleontology. It had a small body, long and slender limbs, an elongated skull with a pointed snout filled with small, sharp teeth, and most strikingly, enormously elongated fourth fingers on each hand, connected to the body by what appeared to be a thin membrane. To a modern observer, the animal is obviously a flying reptile, a pterosaur. But in the 1780s and 1790s, when the fossil was first being studied, the concept of a flying reptile simply did not exist. There was no category for it. There was no mental framework into which it could be placed. The scientists who looked at this fossil were seeing something for which their education and experience had given them no preparation. The first detailed description of the fossil was published by the Italian naturalist Cosimo Alessandro Collini in 1784. Collini recognized that the animal was something extraordinary, but he was deeply uncertain about its nature. He could see the elongated finger and the apparent membrane, but he did not interpret these as wings. Instead, he proposed that the animal was some kind of marine creature. The long finger and membrane, in his view, were not flight surfaces but flippers or paddles, adapted for swimming through water. Collini imagined Pterodactylus as a fully aquatic animal, a strange and unprecedented sea creature that propelled itself through the Jurassic oceans using its membranous appendages. This is a remarkable misinterpretation, and yet it is entirely understandable. Put yourself in Collini's position. You are looking at an animal unlike anything alive today. You can see that it has some kind of membrane attached to its forelimbs. You know of many animals that use membranes or flippers for swimming: seals, sea turtles, various fish. You know of no animal that uses a membrane stretched from a single, enormously elongated finger for flying. The swimming hypothesis is, if you have no other context, a perfectly logical interpretation of the available evidence. But Collini was not the only one struggling with Pterodactylus. Other naturalists weighed in with their own interpretations, and the debate that ensued was one of the most spirited in the history of natural science. Johann Friedrich Blumenbach, a German naturalist and anthropologist, examined the fossil and suggested that it might be some kind of shorebird. The long, pointed skull with its many teeth reminded him, perhaps, of certain wading birds, and the elongated limbs could be seen as adaptations for walking through shallow water. Others proposed that it was a bat, a reasonable guess, given the apparent membrane and the general body proportions, though the teeth and skull were all wrong for a bat. Still others thought it might be some kind of connecting link between birds and mammals, an intermediate form that combined features of both groups. The correct interpretation finally came from the great French anatomist Georges Cuvier, one of the founders of comparative anatomy, and perhaps the most brilliant naturalist of his age. Cuvier examined the fossil in 1801 and recognized it for what it was, a flying reptile. He correctly identified the elongated fourth finger as the support for a wing membrane and recognized that the animal was adapted for aerial locomotion. He named it Pterodactyl, meaning wing finger, a name that would later be Latinized to Pterodactylus. Cuvier's identification was a triumph of comparative anatomy and logical reasoning. He was the first person to correctly understand the basic body plan of a pterosaur, and in doing so, he opened up an entirely new chapter in our understanding of prehistoric life. But even Cuvier did not get everything right. His reconstruction of Pterodactylus, while vastly superior to Collini's aquatic version, still contained significant errors. The precise orientation of the wing membrane, the posture of the animal on the ground, the nature of its skin covering, all of these details were uncertain and would remain so for many years. And the confusion surrounding pterosaurs more broadly would persist long after Cuvier's initial identification. Throughout the 19th century, pterosaurs were variously depicted as bat-like, bird-like, or dragon-like creatures. Some researchers imagined them as soaring, albatross-like flyers. Others depicted them as awkward, ungainly creatures that could barely get off the ground. Still others revived the aquatic hypothesis in modified form, suggesting that pterosaurs might have spent most of their time in or near water, using their wings as fishing aids or as sails. The true picture of pterosaur biology has only begun to come into focus in recent decades, thanks to a combination of new fossil discoveries, advanced imaging techniques, and sophisticated biomechanical analyses. We now know that pterosaurs were highly adapted, active flyers, covered in a fur-like integument called pycnofibers, capable of both sustained soaring and powered flight. Some species were among the largest flying animals ever to have lived, with wingspans exceeding 30 feet. They were not bats. They were not birds. They were not aquatic. They were something entirely unique, a lineage of flying reptiles that evolved flight independently of both birds and bats and dominated the skies for over 160 million years before their extinction at the end of the Cretaceous. But the road from Collini's aquatic paddler to our modern understanding of pterosaurs was long, winding, and paved with mistakes. Every generation of scientists contributed something to the picture, and every generation got something wrong. That is the nature of the endeavor. When you are trying to reconstruct animals that have been dead for 150 million years from nothing more than impressions in stone, perfection is not an option. Progress is the best you can hope for. And progress, in paleontology as in all of science, is messy. The pterodactylus case also raises an important point about the role of existing knowledge in shaping interpretation. Collini did not see a flying reptile because he could not see a flying reptile. The concept did not exist in his mental vocabulary. He saw what his experience and education allowed him to see, an aquatic animal with flipper-like appendages. This is not a personal failing. It is a universal human limitation. We can only interpret new information in terms of the categories and concepts we already possess. When we encounter something truly novel, something that does not fit into any existing category, we either force it into the closest available box or we are paralyzed by confusion. This is why paradigm shifts in science are so difficult and so important. A paradigm shift does not just change the answer to a question. It changes the question itself. Before Cuvier recognized Pterodactylus as a flying reptile, the question was, what kind of aquatic or terrestrial animal is this? After Cuvier, the question became, how did this reptile fly? And are there others like it? The question itself had been transformed, and with it, the entire framework for understanding the fossil. Suddenly, features that had been puzzling or contradictory snapped into focus. The elongated finger was not a flipper but a wing spar. The light, hollow bones were not fragile but aerodynamic. The membrane was not a swimming aid but a flight surface. Everything made sense, but only once you had the right framework. This pattern repeats itself throughout the history of paleontology. The facts do not change, but the interpretation transforms when someone has the insight to ask the right question. Megalosaurus did not change when scientists realized it was bipedal. The same bones that Buckland described in 1824 are the same bones in museum drawers today. What changed was the way those bones were understood. Megarachne did not change when Dunlop reclassified it as a eurypterid. The fossil in Argentina is exactly as it was when Huniken first described it. What changed was the lens through which it was viewed. And Pterodactylus did not change when Cuvier recognized it as a flyer. The exquisite Solnhofen specimen is as it has always been. What changed was the conceptual vocabulary available to the scientists studying it. This is one of the most beautiful and most frustrating aspects of paleontology. The evidence is fixed. It is literally set in stone. But our understanding of that evidence is fluid, dynamic, and constantly evolving. A fossil is not a fact. It is a question. And the answer you get depends entirely on the questions you know how to ask. Let us now turn to what is perhaps the single most spectacular misidentification in the history of paleontology, a case so extraordinary that it almost defies belief. We are going to talk about an animal that was so strange, so utterly unlike anything else on Earth, that its fossils were not merely misidentified. They were split into 3 entirely different organisms, each one assigned to a completely different group of animals. We are going to talk about Anomalocaris. To understand Anomalocaris, we need to go back in time. Way back. Not just millions of years, but hundreds of millions of years, to a period known as the Cambrian, which began approximately 541 million years ago. The Cambrian is one of the most important and most mysterious intervals in the history of life on Earth, because it is during this period that nearly all of the major animal body plans that exist today first appeared in the fossil record. This sudden proliferation of complex animal life, known as the Cambrian explosion, transformed the oceans from relatively simple ecosystems dominated by microbial mats and soft-bodied organisms into diverse, complex communities teeming with predators, prey, and everything in between. The Cambrian explosion is one of the great puzzles of evolutionary biology. How did so many different body plans arise in such a, geologically, short period of time? What environmental or genetic factors triggered this burst of evolutionary innovation? These are questions that scientists are still grappling with today. But for our purposes, the key point is this: the animals of the Cambrian were weird. Profoundly, bewilderingly, almost incomprehensibly weird. They had body plans that do not correspond to anything alive today. They had structures and organs for which we have no modern analog. They were, in many cases, so alien in appearance that the scientists who first encountered their fossils had no idea what they were looking at. Nowhere is this more dramatically illustrated than in the Burgess Shale, a fossil deposit in the Canadian Rockies that has yielded some of the most important Cambrian fossils ever found. The Burgess Shale was discovered in 1909 by the renowned paleontologist Charles Doolittle Walcott, secretary of the Smithsonian Institution. Over the course of several field seasons, Walcott collected tens of thousands of fossils from the site, an extraordinary treasure trove of Cambrian life preserved in exquisite detail. Walcott was a brilliant collector but, by the standards of modern paleontology, a somewhat conservative interpreter. He had a tendency to shoehorn the strange Cambrian animals he found into existing taxonomic categories, assigning them to modern groups even when the fit was poor. This was understandable. Walcott was working within the scientific framework of his time, which held that all animals should be classifiable within known groups, but it led to some significant errors. None was more spectacular than his treatment of Anomalocaris. The story of Anomalocaris and its misidentification is so convoluted that it requires careful telling. Let us take it step by step. The first piece of the puzzle was discovered long before Walcott arrived at the Burgess Shale. In 1892, the paleontologist Joseph Frederick Whitgives described a fossil from the Cambrian rocks of British Columbia that appeared to be the body of a small shrimp or shrimp-like crustacean. The fossil was an elongated, segmented structure with a curved, tapered shape. Whitgives named it Anomalocaris canadensis, the strange shrimp of Canada, because, while it resembled a shrimp in general form, its anatomy did not quite match that of any known crustacean. It was anomalous. It was strange. But it seemed, at least, to be some kind of arthropod, and that was good enough for the time being. What Whitgives had actually found was the frontal appendage of Anomalocaris. These appendages were the large, grasping arms that projected from the front of the animal's head, used for capturing and manipulating prey. Each appendage was segmented, flexible, and lined with sharp spines. In isolation, divorced from the rest of the animal, it did indeed look vaguely like the body of a shrimp or prawn, with the segments of the appendage mimicking the segments of a shrimp's abdomen. The misidentification was understandable but completely wrong. It was not a shrimp. It was an arm. The second piece of the puzzle came from Walcott himself. Among the many fossils he collected from the Burgess Shale were several disc-shaped or ring-shaped structures that appeared to be some kind of jellyfish or medusa. These circular fossils had a radial pattern of overlapping plates, with a central opening. Walcott described them as petoia, a type of jellyfish. It was a reasonable identification. The fossils were round, they appeared to be soft-bodied, and they had the general shape you might expect from a jellyfish preserved in 2 dimensions. But they were not jellyfish. They were mouths. Each disc-shaped fossil was actually the circular mouth apparatus of Anomalocaris, a ring of hard, overlapping plates that could constrict to crush prey. It was a truly extraordinary feeding structure, unlike anything found on any animal alive today. But in isolation, without the rest of the animal attached, it looked for all the world like a jellyfish. The third piece of the puzzle was the main body of the animal. Walcott collected several fossils that showed flattened, oval-shaped organisms with a series of overlapping lateral lobes or flaps along their sides. These he classified as a type of sea cucumber or holothurian, assigning them to the genus Legania. Sea cucumbers are soft-bodied, bottom-dwelling echinoderms, and while the resemblance to a Cambrian anomalocaridid body was tenuous at best, the fossils were soft-bodied and roughly the right shape, and Walcott was working quickly through an enormous backlog of material. So there it was. 3 different fossils. 3 different identifications. A shrimp. A jellyfish. A sea cucumber. 3 separate organisms from 3 different phyla of the animal kingdom. And all 3 were, in reality, parts of a single animal, Anomalocaris, one of the most formidable predators of the Cambrian seas. The truth began to emerge in the 1970s and 1980s, when a new generation of paleontologists re-examined Walcott's Burgess Shale collections with fresh eyes and new interpretive frameworks. The key figures in this re-examination were Harry Whittington, Derek Briggs, and Simon Conway Morris, researchers at Cambridge University who undertook a systematic reinvestigation of the Burgess Shale fauna. Their work, which spanned several decades, fundamentally transformed our understanding of Cambrian life and led to the recognition that many of Walcott's identifications were wrong. The breakthrough with Anomalocaris came when researchers found specimens in which 2 or more of the previously separate organisms were preserved together, in articulation. A specimen might show a shrimp appendage attached to a body, or a jellyfish mouth associated with a set of lateral flaps. When these associated specimens were studied, the truth became inescapable. The shrimp, the jellyfish, and the sea cucumber were all parts of the same animal. They were not 3 organisms. They were one. And what an organism it was! When fully reconstructed, Anomalocaris was revealed to be a large, active, swimming predator, possibly the largest animal in the Cambrian seas. Complete specimens suggest a body length of up to 3 feet, which may not sound impressive by modern standards but was enormous for the Cambrian, when most animals were measured in inches. Anomalocaris had a pair of large, compound eyes, among the most sophisticated visual organs known from the Cambrian, mounted on stalks at the front of its head. Its 2 frontal appendages, the shrimps, were flexible, spiny grasping organs used to capture prey and bring it to the circular mouth. The mouth itself, the jellyfish, was a formidable crushing apparatus capable of processing hard-shelled prey, including trilobites. The body, the sea cucumber, was propelled through the water by undulating the lateral lobes along its sides, in a manner somewhat similar to the swimming of modern cuttlefish or rays. Anomalocaris was, in short, a magnificent and terrifying animal. It was the apex predator of its ecosystem, the great white shark of the Cambrian seas. And for nearly a century, it had been hiding in plain sight in museum collections, disassembled into 3 separate organisms, each one misidentified, each one misunderstood. The Anomalocaris story is perhaps the most extreme example of a theme that runs through all of the cases we have discussed: the danger of interpreting fossils in isolation. A frontal appendage, by itself, looks like a shrimp. A mouth, by itself, looks like a jellyfish. A body, by itself, looks like a sea cucumber. Each piece, taken alone, leads you astray. It is only when you see the pieces together, in context, that the true picture emerges. This is a metaphor for paleontology as a whole. Every fossil is a fragment. Every fragment is ambiguous. The only way to resolve the ambiguity is to find more fragments, and to find ways of connecting them, to each other, to other fossils, to the broader patterns of anatomy and evolution that give individual bones and impressions their meaning. But there is another lesson here too, one that is more uncomfortable. The Anomalocaris misidentification persisted for nearly a century. That is not because the scientists involved were stupid or careless. It is because they were working within a system that, for all its strengths, has certain built-in limitations. Once a fossil receives a name and a classification, that identification tends to persist. Other researchers cite it. Textbooks repeat it. Museum labels display it. The identification becomes part of the received wisdom of the field, and it takes a significant effort to overturn it. This is the weight of authority in science, and while it usually serves to stabilize knowledge and prevent wild swings of interpretation, it can also slow the correction of errors. The re-examination of the Burgess Shale fauna in the 70s and 80s was not just a scientific exercise. It was, in a very real sense, a rebellion against authority, a challenge to the received wisdom that had been handed down from Walcott, one of the most powerful and respected scientists of his generation. The researchers who undertook this re-examination needed not just scientific skill but intellectual courage, because they were, in effect, saying that one of the giants of their field had been wrong. About a lot of things. For a very long time. That kind of courage is essential for the progress of science, but it is never comfortable. And it is worth remembering, as we marvel at the absurdity of a single animal being split into a shrimp, a jellyfish, and a sea cucumber, that the scientists who perpetuated these errors were not fools. They were products of their time, working with the tools and concepts available to them, doing the best they could in the face of genuinely baffling evidence. The Cambrian was, and remains, one of the most challenging periods for paleontologists to study, precisely because the animals of that era are so alien, so far removed from anything in our modern experience, that our usual analogies and reference points break down. Anomalocaris is a reminder that the past is a foreign country, and the deeper into the past we look, the more foreign it becomes. The animals of the Cambrian do not play by the rules we have learned from studying modern ecosystems. They challenge our assumptions about what animals should look like, how they should be built, and how they should live. And when they challenge our assumptions, we make mistakes. That is the cost of doing business in paleontology. But the rewards, the thrill of finally seeing the true face of a creature that has been hiding for 500 million years, make the cost worthwhile. We have now seen a dinosaur mistaken for a lizard, a sea scorpion mistaken for a spider, a dinosaur mistaken for a turtle, a flying reptile mistaken for an aquatic animal, and a single predator disassembled into 3 separate organisms. Each of these cases is extraordinary in its own right. But we have 2 more stories to tell, and the first of them involves one of the most mysterious and most debated fossils of the 20th century. We are going to talk about Dinosaurus. The name Dinosaurus means terrible hand, and when you hear the story of how this animal was discovered, you will understand why. In 1965, a Polish-Mongolian paleontological expedition was working in the Nemegt Formation of the Gobi Desert, the same formation that had yielded Therizinosaurus nearly 2 decades earlier. The expedition, led by the remarkable Polish paleontologist Zofia Kielin-Jaworowska, was one of the most productive in the history of Mongolian paleontology, recovering a wealth of dinosaur, mammal, and other vertebrate fossils that would keep scientists busy for decades. Among the many discoveries made during the expedition was a find that was, by any standard, astonishing. The team uncovered a pair of enormous forelimbs, complete with hands and claws. These arms were, simply put, stupendous. Each arm was approximately 8 feet long, about 2.5 meters. The hands were tipped with massive, curved claws. The arms themselves were powerfully built, with thick bones and large areas for muscle attachment. They were, at the time of their discovery, the largest arms known from any bipedal dinosaur. But here was the problem: the arms were essentially all that was found. The rest of the animal, the skull, the vertebral column, the pelvis, the hind limbs, the tail, was missing. Only the forelimbs and a few associated fragments were recovered. The paleontologists who described the find, Halska Osmalska and A. Voroniewicz, recognized that the arms belonged to some kind of theropod dinosaur, based on certain anatomical features of the bones. They named it Dinosaurus mirificus, the wonderful terrible hand, in 1970. But beyond establishing that it was a theropod, they could say almost nothing about what the animal looked like. And with that, one of the great mysteries of paleontology was born. For nearly 50 years, Dinosaurus was known only from those enormous arms. 50 years. Half a century. During that time, the arms sat in museum collections, inspiring wonder, confusion, and a seemingly endless parade of speculation about what the rest of the animal might have looked like. The speculation was wild, creative, and often completely wrong. Some researchers, noting the size and power of the arms, imagined Dinosaurus as a massive carnivorous theropod, a superpredator even larger than Tyrannosaurus rex, using its tremendous arms to grapple with and subdue enormous prey. This was perhaps the most popular hypothesis, driven by the intuitive assumption that big arms with big claws must belong to a big predator. In this vision, Dinosaurus was the ultimate theropod, a nightmare creature that combined enormous size with devastating four-limb weaponry. Others proposed more exotic interpretations. Some imagined Dinosaurus as a tree-dwelling animal, using its long arms to climb or hang from branches in the manner of a giant sloth. This was a minority view, and for good reason. An animal with 8-foot arms would have needed exceptionally large and strong trees, and the late Cretaceous forests of the Gobi, while significant, were not known for producing trees of sufficient size. But the sloth hypothesis had a certain appeal, if only because it was delightfully bizarre. Still others suggested that Dinosaurus might have been a digging animal, using its massive claws to excavate termite mounds or other underground food sources, in the manner of a modern anteater or pangolin. This hypothesis had the advantage of explaining the large claws without requiring the animal to be a predator, but it suffered from the same problem as many other hypotheses. Without the rest of the skeleton, there was no way to test it. The popular imagination, meanwhile, ran even wilder than the scientific speculation. Dinosaurus became a staple of dinosaur mystery lists, the subject of countless articles, books, and television programs that reveled in the enigma of the terrible hands. Artists produced reconstruction after reconstruction, each one reflecting the biases and assumptions of its creator. Some drew Dinosaurus as a bulky, muscular carnivore with a fearsome skull. Others depicted it as a more gracile, omnivorous animal. Some imagined it with a long neck, others with a short one. Some gave it feathers, others did not. The range of interpretations was a testament to the power of the human imagination and the limitations of working from incomplete evidence. The mystery persisted for so long, and generated so much public interest, that Dinosaurus became something of a celebrity in paleontological circles. It was the great unknown, the dinosaur that refused to reveal itself. Other mysterious dinosaurs were gradually demystified as new fossils came to light, but Dinosaurus remained stubbornly enigmatic. Year after year, decade after decade, the terrible hands kept their secrets. And then, in 2014, everything changed. A team of researchers led by Yong-Nam Lee of the Korea Institute of Geoscience and Mineral Resources published a paper in the journal Nature that finally, definitively revealed the true face of Dinosaurus mirificus. The paper was based on two new, substantially complete specimens that had been recovered from the Nemegt Formation, along with portions of the original specimen that had been illegally collected and sold on the black market but were subsequently recovered and returned to Mongolia. The results were, to put it mildly, unexpected. Dinosaurus was not a superpredator. It was not a sloth. It was not an anteater. It was an ornithomimosaur, a member of the ostrich dinosaur family. But it was an ornithomimosaur unlike any that had been previously imagined. Ornithomimosaurs, as their nickname suggests, are theropod dinosaurs that superficially resemble large, flightless birds. Most known ornithomimosaurs are relatively lightly built animals with long legs, long necks, small heads, and beaked jaws. They are generally thought to have been omnivores, feeding on a combination of plants, small animals, and possibly insects. They are not, by any stretch of the imagination, among the most fearsome dinosaurs. They are the gazelles of the dinosaur world, built for speed and agility rather than brute strength. Dinosaurus was an ornithomimosaur. But it was a deeply weird ornithomimosaur. Where typical ornithomimosaurs were light and gracile, Dinosaurus was massive, weighing an estimated 6 to 7 tons, roughly the size of a large elephant. Where typical ornithomimosaurs had proportionally small heads on long, slender necks, Dinosaurus had a long, deep, duck-billed snout that looked like nothing else in the ornithomimosaur family. Where typical ornithomimosaurs had smooth, streamlined backs, Dinosaurus had a series of elongated neural spines on its vertebrae that would have formed a prominent hump or sail along its back, similar in some ways to the sail of Spinosaurus. And those arms. Those magnificent, terrible, mysterious arms that had haunted paleontology for half a century. They were real. They were every bit as enormous and impressive as they had seemed when they were first discovered. But they were attached to an animal that no one had predicted, a giant, hump-backed, duck-billed ornithomimosaur that probably spent much of its time wading through rivers and lakes, scooping up fish, plants, and whatever else it could find. The final truth about Dinosaurus was stranger than any of the hypotheses that had been proposed during the 5 decades of speculation. It was not the terrifying super-predator that many had imagined. It was not the giant sloth that others had proposed. It was something entirely unexpected, something that defied categorization, something that could not have been predicted from the arms alone because it represented a body plan that was, in many ways, without precedent. And that, perhaps, is the most important lesson of the Dinosaurus story. When you have only a fragment of an animal, you can speculate endlessly about what the rest of it looked like, and you will almost certainly be wrong. Not because your speculation is unintelligent, but because nature is more creative than we are. Evolution does not design animals according to our expectations. It does not follow the templates that we project onto it. It produces forms and combinations that are genuinely novel, genuinely surprising, and genuinely beyond our ability to anticipate from incomplete evidence. The Dinosaurus case also has a darker side that is worth acknowledging. Part of the reason the mystery persisted for so long is that the original site was looted by fossil poachers after the initial discovery. Significant portions of what may have been a more complete skeleton were illegally removed from the quarry and sold on the international fossil black market. Some of this material was eventually recovered through the efforts of law enforcement and the scientific community, but the damage done by the poaching was significant. Key pieces of evidence were lost or scattered, delaying the resolution of the mystery by years or even decades. Fossil poaching is a serious and growing problem worldwide. The illegal trade in fossils not only removes scientifically important specimens from their geological context, destroying crucial information about the animal's environment, associated fauna, and taxonomy, but also contributes to the kind of prolonged scientific uncertainty that we saw with Dinosaurus. Every fossil that is removed from a site without proper documentation is a piece of evidence that can never be fully interpreted. It is a page torn from the book of life, a gap in the narrative that may never be filled. But let us not end the story of Dinosaurus on a dark note. Because the eventual resolution of the mystery, the publication of the 2014 paper and the revelation of the animal's true appearance, was a genuine moment of triumph for paleontology. It was a demonstration of the power of persistence, collaboration, and the scientific method. 50 years of uncertainty, speculation, and frustration culminated in a discovery that was more surprising and more wonderful than anyone had dared to imagine. The terrible hands finally had a body. And what a body it was! Dinosaurus mirificus. The wonderful terrible hand. A dinosaur that defied every prediction, confounded every expectation, and reminded us, once again, that the history of life on Earth is full of surprises. We have now journeyed through a remarkable series of paleontological misadventures, from the very first dinosaur ever named to one of the last great mysteries of the Mesozoic. We have seen how limited evidence, limited conceptual frameworks, and the inherent biases of human cognition can lead even brilliant scientists astray. We have seen how fossils that seem straightforward can conceal depths of complexity that take decades or even centuries to plumb. And we have seen how the correction of errors, while sometimes slow and painful, is a vital and beautiful part of the scientific process. But each of these stories, for all their variety, shares something in common. They are all stories about the difficulty of interpreting the remains of extinct animals, animals that we know existed because their bodies left traces in the rock. They are stories about getting the details wrong, the posture of Megalosaurus, the identity of Megarachne, the body plan of Anomalocaris, the overall appearance of Dinosaurs. In all of these cases, the fundamental question, did this animal exist? Was never in doubt. The fossils were real. The animals were real. The only question was what they looked like and how they lived. But what happens when the fossil record itself is incomplete in a more fundamental way? What happens when the absence of fossils leads us to conclude not merely that an animal looked different from what we thought, but that it is gone entirely? What happens when science declares an animal extinct, and then nature proves science wrong? That is the subject of our final story, and it is perhaps the most humbling of them all. We are going to talk about the coelacanth. The coelacanth story is, in many ways, the ultimate expression of a concept known as the Lazarus taxon. In paleontology, a Lazarus taxon is an organism that disappears from the fossil record for an extended period, sometimes millions of years, and then reappears, either as a new fossil discovery in younger rocks or, in the most dramatic cases, as a living animal. The name comes from the biblical figure of Lazarus, who was raised from the dead. A Lazarus taxon is an organism that science has declared dead, only to have it come back to life. There is no more famous Lazarus taxon than the coelacanth. Coelacanth are lobe-finned fish, members of a group known as the Sarcopterygiae. This group is of profound importance in evolutionary biology, because it is from lobe-finned fish that all terrestrial vertebrates, amphibians, reptiles, birds, and mammals, are ultimately descended. The fleshy, bony fins of Sarcopterygian fish are the evolutionary precursors of the limbs that allowed our distant ancestors to crawl out of the water and onto land. In a very real sense, we are all modified lobe-finned fish. Coelacanth first appear in the fossil record approximately 400 million years ago, during the Devonian period. Over the next 340 million years, they diversified into a wide variety of forms, ranging from small, stream-dwelling species to large, ocean-going predators. They were a successful and long-lived group, surviving through multiple mass extinction events, including the devastating end-Permian extinction that wiped out over 90% of all marine species. But the coelacanth fossil record has a peculiar characteristic. It is, for the most part, quite good for the Paleozoic and Mesozoic eras, with numerous species described from many different geological formations around the world. But it ends, abruptly and completely, at the end of the Cretaceous period, approximately 66 million years ago. The same asteroid impact that wiped out the non-avian dinosaurs, the pterosaurs, the marine reptiles, and many other groups also, apparently, exterminated the coelacanth. At least, that is what the fossil records seem to indicate. For more than a century, the coelacanth was treated as a textbook example of an extinct group. Its fossils were studied, described, classified, and placed in the evolutionary tree of life. Paleontologists traced the history of the group from its origins in the Devonian to its apparent extinction at the end of the Cretaceous. The coelacanth was dead. The science was settled. And then, on December 22, 1938, everything changed. On that date, a South African museum curator named Marjorie Courtney Latimer received a phone call from a local fisherman named Hendrik Goosen, the captain of the trawler Nering. Goosen had been fishing off the mouth of the Columna River, near the town of East London on the southeast coast of South Africa, and his nets had brought up a fish unlike anything he or his crew had ever seen. It was large, about 5 feet long, and heavy, weighing over 120 pounds. Its scales were thick and bony, unlike the thin, overlapping scales of most modern fish. Its fins were fleshy and lobed, supported by internal bony structures. And its color was a striking, iridescent blue. Courtney Latimer went to see the fish. She was not a fish specialist, but she had a keen eye for the unusual, and she immediately recognized that this was something extraordinary. She later described her first reaction in vivid terms. She knew, instinctively, that this was a fish of great scientific importance, even though she could not identify it. She arranged for the specimen to be preserved, no easy feat in the South African summer heat, without access to adequate refrigeration, and then she began the process of finding someone who could tell her what she had found. She turned to James Leonard Brearley Smith, a chemistry professor at Rhodes University who was also an avid amateur ichthyologist. Smith was a meticulous, passionate student of fish, and when he saw the specimen, or rather, when he saw the rough sketch and description that Courtney Latimer sent him by letter, his reaction was immediate and electrifying. He recognized the fish at once. It was a coelacanth. A living coelacanth. An animal that had been presumed extinct for 66 million years was swimming in the Indian Ocean. Smith's reaction, when he confirmed the identification in person, was one of profound shock. He later wrote that he would not have been more surprised if I had seen a dinosaur walking down the street. The discovery was, without exaggeration, one of the most astonishing zoological events of the 20th century. Here was an animal that had been officially extinct for longer than the entire age of mammals, gone since before the first primates evolved, since before the first horses galloped across the plains, since before the first whales returned to the sea, and it was alive. It had been alive the whole time. Swimming quietly in the deep waters of the Indian Ocean, minding its own business, while generations of scientists confidently wrote it off as a victim of the end Cretaceous mass extinction. Smith named the living coelacanth Latimeria columni, in honor of Marjorie Courtney Latimer, and the river near which the fish had been caught. The discovery made headlines around the world. It was front-page news on every continent. It captured the public imagination in a way that few scientific discoveries ever do, because it touched on something deep and primal in the human psyche, the idea that the past is not dead, that the creatures of ancient epochs might still be out there, lurking in the unexplored corners of the world, waiting to be found. But the scientific significance of the discovery went far beyond its emotional impact. The living coelacanth provided an unprecedented opportunity to study the anatomy, physiology, and behavior of a group of fish that had previously been known only from fossils. And what scientists found when they studied Latimeria was remarkable. The living coelacanth is, in many ways, a window into the deep past. Its basic body plan has changed remarkably little since the Cretaceous. Its lobed fins, its thick scales, its unique joint in the middle of its skull, the intracranial joint, which allows the front part of the skull to tilt upward when the fish opens its mouth, its specialized electroreceptive organ in the snout, all of these features were familiar from the fossil record and were now available for study in a living animal. But Latimeria also revealed features that could never have been inferred from fossils alone. Its blood is remarkably low in hemoglobin, suggesting a low-energy lifestyle. Its metabolic rate is extremely slow, even by fish standards. It is ovoviviparous, meaning that it gives birth to live young that develop from eggs retained inside the mother's body. It is a nocturnal animal, spending the day resting in underwater caves and emerging at night to feed on fish and squid. It uses its lobed fins in a distinctive, alternating pattern that has been compared to the gait of a tetrapod walking on land, a living echo of the evolutionary transition from water to land that occurred hundreds of millions of years ago. All of these details were invisible in the fossil record. Fossils can tell you about an animal's bones, its teeth, its overall size and shape. But they cannot tell you about its blood chemistry, its reproductive strategy, its daily habits, or the color of its skin. The discovery of a living coelacanth opened up an entirely new dimension of understanding, one that would have been impossible without the living animal. But the coelacanth story also raises troubling questions about the reliability of the fossil record. If a large, conspicuous fish like the coelacanth could survive undetected for 66 million years, leaving no trace whatsoever in the fossil record during that entire period, how many other supposedly extinct animals might still be out there? And how much can we really trust the fossil record as a guide to what is and is not alive? The answer to these questions is nuanced. The fossil record is not a complete census of life on Earth. It never has been and never will be. The overwhelming majority of organisms that have ever lived left no fossil trace whatsoever. Fossilization requires a very specific set of circumstances: rapid burial, the right chemical environment, the right type of sediment, and most organisms are never exposed to those circumstances. Marine organisms are more likely to be fossilized than terrestrial ones, because ocean sediments are more conducive to preservation. Hard-bodied organisms are more likely to be fossilized than soft-bodied ones, because bones, shells, and teeth resist decomposition. Large organisms are more likely to be fossilized than small ones, because their remains are more conspicuous and more durable. But even within these broad patterns, the fossil record is full of gaps. Entire ecosystems can exist for millions of years without leaving any fossil trace, if the local conditions are not favorable for preservation. Deep-sea environments, for example, are notoriously poor at producing fossils, because the sediments in the deep ocean are subject to intense pressure and geological activity that destroy organic remains. This is precisely the environment where modern coelacanth live, in deep waters, along steep, rocky slopes, in areas where fossilization is extremely unlikely. So the coelacanth's 66 million year absence from the fossil record is not evidence that the fish was not there. It is evidence that the fish was living in an environment that does not produce fossils. The Lazarus effect is not a miracle. It is a predictable consequence of the incompleteness of the fossil record. When an organism inhabits an environment that is poorly sampled by the fossil record, it can disappear from the geological sequence even though it is still alive and well. This has profound implications for how we think about extinction. When a paleontologist says that a group of organisms went extinct at a particular time, what they are really saying is that the group disappears from the fossil record at that time. These are not the same thing. Disappearance from the fossil record is a necessary condition for extinction. If an animal is alive, it can potentially leave fossils, but it is not a sufficient condition. The animal might still be out there, in an environment that does not preserve its remains. This does not mean that we should doubt every extinction event in the geological record. The vast majority of disappearances from the fossil record are genuine extinctions. When the non-avian dinosaurs vanish from the rock record at the end of the Cretaceous, they really are gone. We are as certain of this as we are of anything in paleontology. The evidence is overwhelming, consistent, and global. But the coelacanth serves as a cautionary tale. It reminds us that the fossil record, for all its power and beauty, is an imperfect document. It has gaps, biases, and blind spots. It can mislead us about the timing and completeness of extinctions. And it can, on rare and wonderful occasions, be proven wrong by the discovery of a living animal that was supposed to have died out millions of years ago. The coelacanth is still with us today, swimming in the deep waters off the coasts of Africa and Indonesia. It is a rare animal, probably numbering in the low thousands, and it is critically endangered by the pressures of modern fishing and habitat disruption. But it is alive. After 400 million years of evolution, after surviving every mass extinction that the planet has thrown at it, after spending 66 million years hiding from science in the deep ocean, the coelacanth is still here. And its survival carries a message that transcends paleontology. It tells us that the natural world is full of surprises. It tells us that our knowledge, however vast and however carefully accumulated, is always incomplete. It tells us that humility is not just a virtue in science, it is a necessity. And it tells us that life, in all its stubborn, tenacious, endlessly creative glory, has a way of defying our expectations. We have now traveled through some of the greatest misidentifications, misinterpretations, and misjudgments in the history of paleontology. From the lizard-like Megalosaurus to the spider that was not a spider, from the turtle that was really a dinosaur to the aquatic creature that actually flew, from the single animal that became 3 separate species to the mysterious arms that defied explanation for half a century, and finally to the fish that refused to stay extinct. Each of these stories is unique, but together they paint a portrait of a science that is defined by its relationship with uncertainty. Paleontology is not a science of certainty. It is a science of probability, of inference, of educated guessing backed by the best available evidence. The evidence is always incomplete. The guesses are always subject to revision. And the history of the field is, in many ways, a history of getting things wrong and then, gradually, painstakingly, getting things a little more right. This is not a weakness. It is a strength. A science that never makes mistakes is a science that never takes risks, never pushes boundaries, never ventures into unknown territory. Paleontology, by its very nature, is always venturing into unknown territory. Every new fossil is a step into the dark. Every interpretation is a hypothesis, offered in good faith, subject to testing and revision. The willingness to be wrong, and to admit it when the evidence demands it, is what makes paleontology a science rather than a mythology. And the stories we have told today are not stories of failure. They are stories of the process by which science corrects itself. They are stories of the long, slow, sometimes frustrating, but ultimately triumphant journey from ignorance to understanding. They are reminders that the truth about the past is not handed to us on a silver platter. It has to be earned, piece by painstaking piece, fossil by fragmentary fossil, mistake by illuminating mistake. The past is not dead. It is not even past. It lives in the rocks beneath our feet, in the bones and shells and impressions left behind by billions of years of life. And every time we dig into those rocks, every time we pull out a fragment of ancient bone and hold it up to the light, we are engaging in one of the most profound and most humbling acts of which the human mind is capable. The act of reaching across the abyss of time and touching something that lived and breathed and moved through a world that we can barely imagine. We will get things wrong. We always have. We always will. But we will also, eventually, get things right. And the journey from wrong to right, that journey of discovery, of correction, of ever-deepening understanding, is, in the end, the greatest story that paleontology has to tell. We ended part 1 with a promise. A promise to go deeper. A promise to peel back the layers of these extraordinary stories and examine not just what went wrong, but why it went wrong, how it was eventually set right, and what all of it tells us about the way we understand the deep past. We have already walked through 6 of the most remarkable misidentifications in the history of paleontology, from the very first dinosaur ever named to a fish that science declared dead for 66 million years. But every one of those stories has more to tell. Every one of them contains lessons that extend far beyond the individual animal, far beyond the individual mistake, into the very heart of how science works, how it fails, and how it ultimately triumphs. So let us return to where we began. Let us go back to the beginning and look again, this time with sharper eyes and deeper understanding. When William Buckland stood before the Geological Society of London in 1824, and presented his description of Megalosaurus, he was not just describing a fossil. He was attempting something that had never been done before. He was trying to reconstruct a vanished world from fragments of bone. He was trying to bring the dead back to life, at least in the imagination. And the tools he had at his disposal, comparative anatomy, geological context, and his own formidable intellect, were, for all their power, desperately inadequate for the task. We discussed in part 1 how Buckland imagined Megalosaurus as a massive, sprawling, quadrupedal lizard, and how Richard Owen later reimagined it as an elephant-like quadruped. But what we did not fully explore is the deeper question of why these reconstructions persisted for so long. It was not simply a matter of ignorance. It was a matter of infrastructure, the entire intellectual apparatus that surrounded the study of fossils in the 19th century. Consider the state of comparative anatomy in Buckland's time. The science of comparing the skeletal structures of different animals was still in its infancy. Georges Cuvier had pioneered the field, establishing the principle that the different parts of an animal's body are functionally integrated, that you can, in theory, infer the shape of an entire animal from a single bone, because each bone reflects the functional demands placed on the whole organism. This was a revolutionary insight, and it gave paleontologists a powerful tool for reconstructing extinct animals. But it was also a tool that could be misused, especially when the extinct animal in question had no close living analog. Buckland used comparative anatomy to reconstruct Megalosaurus, but the comparisons he drew were with living reptiles, lizards, crocodiles, and other animals that walk on 4 legs with a sprawling gait. These were the only large reptiles he knew. He had no reason to suspect that there had once existed an entirely different type of reptile, one that walked upright on two legs like a bird. The concept of a bipedal reptile was not just unknown, it was inconceivable. It lay outside the boundaries of what the existing framework of comparative anatomy could predict. This is a subtle but crucial point. Comparative anatomy works by analogy. It says, this extinct animal has bones similar to this living animal, therefore the extinct animal probably moved and lived in a similar way. When the analogy is close, when the extinct animal is genuinely similar to a living one, this approach works beautifully. But when the extinct animal is fundamentally different from anything alive today, the approach breaks down. The analogy leads you astray, because there is nothing in the modern world to compare the fossil to. This is exactly what happened with Megalosaurus. Buckland compared its bones to those of modern lizards and concluded that it was a giant lizard. Owen compared its bones to those of modern mammals and concluded that it was an elephant-like reptile. Both were wrong, because neither had access to the correct analogy. The correct analogy, a large, bipedal, ground-running bird, was not recognized as relevant until much later, when more complete theropod skeletons revealed the bird-like posture and locomotion of these animals. The lesson here is profound. Comparative anatomy is one of the most powerful tools in paleontology, but it is only as good as the database of comparisons available. When the database is incomplete, when it lacks the living animals that most closely resemble the extinct one, the tool can mislead. And in the 19th century, the database was profoundly incomplete. Scientists knew about lizards, crocodiles, turtles, and mammals. They did not know about bipedal theropods, because bipedal theropods were exactly the thing they were trying to discover. It was a catch-22. You cannot correctly reconstruct an animal you have never imagined, and you cannot imagine an animal you have never correctly reconstructed. This circular problem was eventually broken by the accumulation of evidence. As more and more theropod skeletons were discovered over the course of the 19th and early 20th centuries, Allosaurus, Ceratosaurus, Tyrannosaurus, and many others, the bipedal body plan became undeniable. The evidence forced scientists to expand their conceptual framework, to add a new category to their mental vocabulary, the bipedal predatory reptile. Once that category existed, the old reconstructions of Megalosaurus became obviously wrong. But the category could only come into existence after enough evidence had accumulated to make it inescapable. This is how paradigm shifts work in science. They are not sudden flashes of insight that come from nowhere. They are the gradual, often reluctant recognition that the existing framework cannot accommodate the evidence. The evidence accumulates, the contradictions mount, and eventually, someone has the courage or the clarity to say, our framework is wrong. We need a new one. In the case of bipedal dinosaurs, this process took the better part of a century. It was slow, it was contentious, and it was marked by fierce debates and personal rivalries. But it was also, ultimately, successful. The old lizard-like and elephant-like reconstructions were abandoned, and a new, more accurate picture of theropod dinosaurs took their place. But the story of Megalosaurus has a final twist that is worth noting. Even today, 200 years after Buckland's original description, Megalosaurus remains one of the most poorly known of all dinosaur genera. The original specimens are fragmentary and difficult to interpret. The animal's exact size, appearance, and ecological niche are still debated. Other theropods from the same general group, the Megalosauridae, are better known from more complete specimens, and much of what we know about Megalosaurus is actually inferred from these relatives rather than from the original material. This is a common situation in paleontology. The first-named members of a group are often the worst known, because they were discovered and described at a time when the tools and techniques for studying fossils were least developed. Later discoveries, made with better tools and a better understanding of anatomy, often yield far more information. The irony is that the animal that lends its name to the group, the type genus, in taxonomic terminology, is frequently the one we understand the least. Megalosaurus is, in a sense, the poster child for this irony. It was the first. It was the most famous. And it remains, in many ways, the most mysterious. The great lizard that started it all is still hiding in the shadows, 2 centuries on. Let us now return to the Carboniferous and to the case of Megarachne, the spider that was not a spider. In Part 1, we told the story of how this fossil was originally identified as the largest spider in history and later reclassified as a eurypterid. But there is more to this story than a simple misidentification. The Megarachne case illuminates a broader set of issues about how scientific knowledge is communicated, how errors propagate, and how the relationship between science and popular culture can both help and hinder the pursuit of truth. When Mario Hunican published his original description of Megarachne in 1980, the paper appeared in a Spanish-language Argentine scientific journal. This is not unusual. Scientists publish in the journals that serve their professional communities, and South American paleontologists naturally publish in South American journals. But it did mean that the paper was not immediately accessible to the broader international community. Many researchers who might have been able to challenge the spider identification simply never read the original description. They encountered Megarachne not through the primary literature but through secondary sources, popular science books, magazine articles, television documentaries, that presented the spider identification as established fact. This is a critical point. In the modern scientific ecosystem, primary research papers are the foundation of knowledge. They contain the detailed descriptions, measurements, photographs, and arguments that allow other scientists to evaluate the evidence and form their own conclusions. But most people, including many scientists working in adjacent fields, do not read primary research papers on a regular basis. They rely on secondary sources, textbooks, review articles, popular science writing, and media coverage. These secondary sources are essential for disseminating knowledge, but they also introduce a filtering effect. The nuances, caveats, and uncertainties of the original paper are often smoothed over or omitted entirely. What reaches the public is not the careful, qualified language of the scientist but the bold, definitive language of the journalist or the documentary narrator. In the case of Megarachne, this filtering effect was devastating. The original paper, while presenting the spider identification as a hypothesis, also acknowledged certain difficulties and uncertainties. But by the time the story reached the popular media, those uncertainties had vanished. Megarachne was not presented as a fossil that might be a giant spider. It was presented as the largest spider that ever lived. Full stop. No qualifications. No caveats. No mention of the possibility that the identification might be wrong. This is how scientific errors become entrenched in popular culture. A tentative hypothesis, offered in good faith by a researcher working with limited evidence, is translated into a definitive statement by the media. The definitive statement is repeated in books, articles, and documentaries. It becomes common knowledge. And once something becomes common knowledge, it is extraordinarily difficult to correct, even when the original hypothesis is overturned by new evidence. The reclassification of Megarachne as a eurypterid in 2005 was published in a high-profile journal and received widespread attention in the scientific community. But its impact on popular culture was much slower and more uneven. For years after the reclassification, the spider version of Megarachne continued to appear in books, websites, and even museum exhibits. Some of these references were simply outdated materials that had not been revised. But others represented active resistance to the correction, a reluctance to give up a good story in favor of a less exciting truth. This resistance is not unique to Megarachne. It is a pervasive problem in the communication of science to the public. Corrections are less interesting than original claims. A headline that says, "Giant spider discovered," will always attract more attention than a headline that says, "Giant spider reclassified as sea scorpion." The initial discovery generates excitement, wonder, and perhaps a delicious shiver of fear. The correction generates, well, mostly just confusion and mild disappointment. This asymmetry between discovery and correction is one of the great challenges of science communication. How do you make corrections as compelling as original discoveries? How do you persuade people to update their beliefs in light of new evidence? These are not just academic questions. They go to the heart of how a scientifically literate society functions. And the Megarachne case, for all its apparent simplicity, is a powerful illustration of these challenges. There is another aspect of the Megarachne story that deserves further exploration: the question of preservation bias. Megarachne was preserved as a flattened impression in rock, which means that much of its three-dimensional structure was lost. Features that might have been clearly distinguishable in a three-dimensional specimen, the detailed morphology of the appendages, the structure of the body segments, the shape of the mouthparts, were compressed into a two-dimensional plane, making them ambiguous and difficult to interpret. Preservation bias is one of the most pervasive and insidious sources of error in paleontology. Fossils are not photographs of living animals. They are the end products of a long and often violent process of death, decay, burial, compression, and mineralization that can radically alter the appearance of the original organism. A round structure can be flattened into an oval. A three-dimensional body can be compressed into a flat disk. Delicate features can be destroyed entirely, leaving behind only the most robust elements of the anatomy. The paleontologist who studies such a fossil is not looking at the animal as it was in life. They are looking at a distorted, degraded, incomplete version of it, a version that may bear only a passing resemblance to the original. Interpreting this distorted image requires a deep understanding of taphonomy, the science of what happens to an organism between death and discovery, and a willingness to acknowledge the limits of what the preserved material can tell you. In the case of Megarachne, the flattened preservation obscured the very features that would have allowed a correct identification. The detailed structure of the appendages, which would have clearly distinguished a eurypterid from a spider, was lost or ambiguous. The overall body shape, compressed into two dimensions, was compatible with either interpretation. The preservation, in short, created a Rorschach test, a pattern ambiguous enough to support multiple readings, depending on the expectations and expertise of the viewer. This is a fundamental challenge in paleontology, and it is one that is not easily overcome. Better imaging techniques, CT scanning, synchrotron radiation, and other advanced methods, have dramatically improved our ability to extract information from poorly preserved fossils. But even the most sophisticated technology cannot recover information that was never preserved in the first place. Some fossils are simply too degraded, too compressed, or too incomplete to yield definitive answers. In such cases, the only honest response is to acknowledge the uncertainty and to resist the temptation to present ambiguous evidence as conclusive proof. Megarachne teaches us that the desire for certainty can be the enemy of truth. The world wanted a giant spider. Scientists wanted a giant spider. The fossil was ambiguous enough to support the identification if you approached it with the right expectations. And so a giant spider was born, not from evidence, but from desire. It took 25 years and a team of dedicated researchers to correct the error, and even then, the correction was slow to take hold in the popular imagination. Let us carry this lesson forward as we continue our journey through the annals of paleontological error. The story of Dinosaurs, which we introduced in Part 1, becomes even more fascinating when we examine it in the context of the broader history of dinosaur paleontology in Central Asia. The Gobi Desert is one of the most important paleontological regions on Earth, but it is also one of the most politically complex. For much of the 20th century, access to Mongolian fossil sites was controlled by the Soviet Union and its allies, and the scientific study of Gobi fossils was dominated by Soviet and Mongolian researchers, with limited input from Western scientists. This political isolation had significant consequences for the interpretation of Gobi fossils. Soviet paleontologists, while highly skilled, were working somewhat independently of the broader international community. Their publications appeared primarily in Russian and Mongolian journals, which were not widely read in the West. Their interpretive frameworks, while rigorous, sometimes diverged from those used by Western researchers. And their access to comparative material, fossils from other parts of the world that might have provided useful context for understanding Gobi specimens, was sometimes limited by political barriers. Yevgeny Malev's identification of Dinosaurs as a giant turtle must be understood in this context. Maleev was not working in a vacuum, but he was working in a relatively insular scientific environment. The fossils he was studying were unlike anything in his experience, or in the experience of his colleagues. The comparative material available to him, the other dinosaurs and reptiles known from the Gobi and from other Soviet collections, did not include anything that closely resembled the bizarre morphology of Therizinosaurus. Without access to a broader comparative framework, the turtle hypothesis was, if not convincing, at least defensible. It is worth pausing here to consider just how strange the claws of Therizinosaurus must have appeared to Maleev. Each claw was roughly 70 centimeters long, nearly 2.5 feet. They were gently curved, flattened from side to side, and tapered to a point. They were not the sharp, strongly curved, blade-like claws of a typical theropod predator. They were more like elongated, flattened sickles. There was nothing in the known dinosaur fauna of the time that possessed claws of this size or shape. Now, imagine trying to figure out what kind of animal carried these claws. You have no skull. You have no legs. You have no vertebrae to speak of. You have these enormous, flat, curved claws, and you have the arm bones that supported them. The arms are long and robust, with large muscle attachment sites. The claws show no evidence of being particularly sharp or well-suited for cutting flesh. They seem, if anything, more suited for raking or pulling, for gathering vegetation, perhaps, or for stripping bark from trees. What would you think? What framework would you reach for? Maleev reached for the turtle framework. The flattened shape of the claws reminded him of the broad, flattened claws of certain sea turtles, which used their claws for digging nesting sites and for clinging to rocks. The robustness of the arm bones was consistent with an aquatic animal that used its forelimbs for propulsion. The broad, flat ribs, which were among the few non-arm elements preserved, could be interpreted as part of a turtle-like shell or carapace. It was wrong. But it was not crazy. It was the best fit that Maleev could find within the taxonomic categories available to him. And the key phrase there is, available to him. The category that would have provided the correct fit, herbivorous theropod, did not exist in Maleev's time. It was not until the 1970s and 80s, when Rinchen Barsbold and other Mongolian paleontologists described a series of related animals, that the concept of a herbivorous theropod began to take shape. The gradual emergence of the therizinosaur concept is one of the great detective stories in paleontology. It unfolded over decades, involving researchers from multiple countries, working with fragmentary and often confusing material. Each new discovery added a piece to the puzzle, but the pieces did not always fit together neatly. There were false starts, dead ends, and fierce disagreements. Some researchers argued that therizinosaurs were not theropods at all but belonged to an entirely separate lineage of dinosaurs. Others proposed that they were related to prosauropods, the early, long-necked relatives of the giant sauropods. Still others suggested that they might be some kind of aberrant ornithischian. The debate was resolved, gradually and sometimes painfully, by the application of cladistic analysis, a method of determining evolutionary relationships by comparing shared anatomical features across a wide range of species. Cladistic analyses consistently place therizinosaurs within the theropod clade, specifically as close relatives of the oviraptorosaurs and other Megarachne theropods. This was a surprising result, because therizinosaurs look nothing like typical Megarachnes. They are large, heavy-bodied, pot-bellied animals with small heads, leaf-shaped teeth, and short, stocky legs, about as different from a sleek, agile velociraptor as you can imagine while still being in the same general branch of the family tree. But cladistic analysis does not care about superficial appearances. It cares about shared derived characters, specific anatomical features that are shared by two or more species because they inherited those features from a common ancestor. And when the anatomical details were examined carefully, therizinosaurs turned out to share a suite of derived features with other Megarachne theropods that could not be explained by convergent evolution. They were theropods. Weird, wonderful, deeply unconventional theropods, but theropods nonetheless. The recognition of therizinosaurs as herbivorous theropods was a paradigm shift in its own right. For over a century, the word theropod had been essentially synonymous with Carnivorous dinosaur. Theropods were the predators of the Mesozoic, the tyrannosaurs, the allosaurs, the dromaeosaurs, the hunters and the killers. The idea that some theropods had abandoned meat-eating and become herbivores was radical and, to many, deeply counterintuitive. It was as if someone had discovered a lineage of cats that had evolved to eat grass. But evolution does not respect our expectations. It does not follow the neat categories that we impose upon it. The therizinosaurs are a vivid reminder that evolution is a process of exploration, not of design. Natural selection does not have a plan. It does not know where it is going. It simply favors whatever works, whatever allows an organism to survive and reproduce in its particular environment. And in the late Cretaceous of Central Asia, what worked, apparently, was a theropod that ate plants. A theropod with a big belly, a small head, and enormous claws for pulling down branches or defending against predators. A theropod that Maleev, had he lived to see the full picture, would scarcely have believed. The Therizinosaurus story also illustrates the importance of international collaboration in paleontology. For decades, the study of Gobi fossils was hampered by political barriers that limited the flow of information and expertise between Soviet, Mongolian, and Western scientists. The resolution of the Therizinosaur mystery was made possible, in part, by the opening of these barriers in the late 20th century, which allowed for a more global, more collaborative approach to the study of Central Asian fossils. Joint expeditions involving researchers from Mongolia, Japan, South Korea, and various Western countries produced a wealth of new discoveries that provided the comparative context needed to correctly interpret the bizarre anatomy of therizinosaurs. This is a pattern that repeats itself throughout the history of paleontology. Scientific progress is accelerated by collaboration and impeded by isolation. When researchers from different institutions, different countries, and different traditions can work together, share materials, and challenge each other's ideas, the science moves forward more quickly and more accurately. When barriers, political, linguistic, institutional, or personal, prevent this collaboration, errors persist, mysteries linger, and the full picture takes longer to emerge. The Gobi Desert still holds secrets. New expeditions continue to uncover new fossils, and the story of the therizinosaurs is still being written. But the basic outline is now clear. These were not turtles. They were not sauropods. They were not ornithischians. They were theropods, the most improbable, most surprising, most delightfully bizarre theropods that evolution ever produced. And it took the collective effort of an international community of scientists, working across decades and across borders, to figure that out. Let us now return to the skies and to the case of Pterodactylus. In Part 1, we described how this animal was variously interpreted as an aquatic creature, a shorebird, a bat, and finally, correctly, as a flying reptile. But the story of pterosaur misunderstanding extends far beyond the initial identification of Pterodactylus. For more than 2 centuries after Cuvier's breakthrough, the popular image of pterosaurs remained distorted, inaccurate, and often absurdly wrong. The problem was not that scientists did not know pterosaurs were flyers. Cuvier had established that in 1801, and no serious researcher challenged it thereafter. The problem was that the details, the specific mechanics of pterosaur flight, the nature of their wing membranes, the structure of their bodies, their behavior, their ecology, remained deeply uncertain for a very long time. For much of the 19th and 20th centuries, pterosaurs were depicted as awkward, clumsy flyers, barely able to get airborne and incapable of sustained flight. This image was driven in part by analogy with bats, which were the most familiar membrane-winged flyers. But bats are mammals, and their flight apparatus is fundamentally different from that of pterosaurs. Bats have membranes stretched between 4 elongated fingers and their hind limbs. Pterosaurs had membranes supported primarily by a single, enormously elongated 4th finger, with a different attachment geometry and a different mechanical profile. The bat analogy led to several specific errors. First, it led to the assumption that pterosaurs' wing membranes were attached to their hind limbs, creating a broad, bat-like wing surface. While some evidence supports a hind limb attachment for the wing membrane in certain pterosaur species, the details are complex and vary between groups. Early reconstructions that depicted pterosaurs with broad, bat-like wing membranes connecting their hands to their ankles or even to their tails were oversimplifications at best and outright errors at worst. Second, the bat analogy led to the assumption that pterosaurs were poor walkers. Bats are notoriously ungainly on the ground, shuffling along on their folded wings and tiny hind feet. If pterosaurs were similar to bats, the reasoning went, they too must have been clumsy on the ground, perhaps even incapable of walking at all, spending their entire lives clinging to cliffs and tree branches between flights. This image of the pterosaur as a reluctant, cliff-hanging creature, launching itself into the air only with great effort, persisted well into the 20th century. It was wrong. Modern analyses of pterosaur anatomy, biomechanics, and trackways, yes, pterosaur footprints exist, and they are extraordinarily informative, have revealed that many pterosaurs were actually quite competent walkers. The large as darked pterosaurs, such as Quetzalcoatlus, may have spent a significant portion of their time on the ground, stalking prey on foot like enormous, long-legged storks. Their hind limbs were well suited for terrestrial locomotion, and their wing fingers could fold up neatly, allowing the forelimbs to function as walking appendages in a quadrupedal gait. Third, the bat analogy led to a profound underestimation of pterosaur flight capabilities. Bats are agile flyers, but they are small animals, and their flight is powered primarily by muscle. Pterosaurs, by contrast, included species that were among the largest flying animals ever to have existed, with wingspans exceeding 30 feet. For years, scientists struggled to explain how animals of this size could fly. Some proposed that the largest pterosaurs were too heavy to fly and must have been flightless. Others suggested that they could only fly in the denser atmosphere of the Mesozoic, which might have had a higher oxygen content than today's atmosphere. Still others proposed that they were not true flyers but gliders, dependent on thermal updrafts and unable to sustain powered flight. All of these proposals underestimated pterosaurs. Modern biomechanical analyses, using sophisticated computer models and engineering principles, have shown that even the largest pterosaurs were capable of powered flight. Their bones were incredibly lightweight, hollow, thin-walled, reinforced with internal struts, like the structural engineering of a modern aircraft. Their wing membranes were not simple sheets of skin but complex, layered structures reinforced with internal fibers called actinofibrils, which gave the membrane structural integrity and allowed the pterosaur to control its shape during flight. Their flight muscles were powerful and their cardiovascular systems were efficient. They were not awkward, reluctant flyers. They were superb ones. The most dramatic revision in our understanding of pterosaur biology has come from the discovery of pycnofibers, the fur-like filaments that covered the bodies of many pterosaurs. These filaments, first described in detail from exceptionally preserved specimens in the 1970s and 80s, demonstrate that pterosaurs were not naked, scaly reptiles but were covered in a dense, insulating coat of fibrous material. This discovery had profound implications for our understanding of pterosaur physiology. An animal with an insulating body covering is almost certainly warm-blooded, or at least endothermic, capable of generating its own body heat. This means that pterosaurs were not cold-blooded, sluggish, reptilian flyers but active, high-energy animals with metabolic rates comparable to those of modern birds and mammals. The transformation of pterosaurs from clumsy, cold-blooded, bat-like creatures to active, warm-blooded, sophisticated flyers is one of the great revolutions in paleontological understanding. It happened not through a single discovery but through the accumulation of evidence from multiple lines of research: biomechanics, histology, ichnology, the study of trace fossils, including footprints, and the discovery of new, exceptionally preserved specimens from localities around the world. And yet, the old image persists. In movies, in television, in popular culture, pterosaurs are still often depicted as screeching, leathery, dragon-like creatures that snatch up hapless humans in their talons. They are shown as monsters, not as animals. The nuanced, fascinating reality of pterosaur biology, the pycnofibers, the complex wing membranes, the efficient flight mechanics, the diverse ecological roles, is rarely reflected in popular media. This gap between scientific understanding and popular perception is not unique to pterosaurs. It is a pervasive feature of how paleontology is communicated to the public. The science moves forward, but the public image often remains frozen at a point decades or even centuries behind the current state of knowledge. The crystal palace Megalosaurus, the bat-winged pterodactyl, the tail-dragging Tyrannosaurus. These outdated images have a cultural inertia that resists updating, even as the science that produced them has long since moved on. Closing this gap is one of the great challenges facing paleontology today. And it is a challenge that requires not just better science communication, but a fundamental rethinking of how scientific knowledge reaches the public. It requires scientists who are willing to engage with popular media, artists who are willing to stay current with the latest research, and audiences who are willing to update their mental images in light of new information. It is, in short, a challenge that belongs to everyone. But let us return to the specific case of Pterodactylus and draw one more lesson from it. The initial misidentification of this animal as an aquatic creature was not just a failure of interpretation. It was a failure of imagination. Collini, the first person to describe the fossil in detail, could not imagine a flying reptile because no such thing existed in his experience. His failure was not one of intelligence but of vision. He could not see what he did not know to look for. This is a recurring theme in the history of science. The greatest discoveries are often not the ones that require the most intelligence but the ones that require the most imagination, the ability to conceive of possibilities that lie outside the current framework of understanding. Cuvier saw a flying reptile where Collini saw a swimmer because Cuvier was willing to entertain a possibility that Collini was not. Cuvier did not have better evidence. He had a better imagination. Imagination in science is not the same as fantasy. It is disciplined imagination, the ability to generate hypotheses that are both novel and testable, that push the boundaries of what is considered possible while remaining grounded in evidence. It is the ability to ask, what if the world is different from what I think it is? What if this fossil represents something I have never seen before, something that does not fit into any existing category? What if I am wrong about everything I think I know? These are uncomfortable questions. They require intellectual humility and a willingness to be surprised. But they are the questions that drive science forward. And they are the questions that, throughout the history of paleontology, have turned mistakes into discoveries. The Anomalocaris saga, which we explored at length in Part 1, deserves further examination for what it reveals about the nature of Cambrian life and the unique challenges it poses for paleontologists. The Cambrian explosion, the rapid diversification of complex animal life that began approximately 541 million years ago, produced a menagerie of organisms so bizarre, so alien, so fundamentally different from anything alive today that they strain the very limits of our ability to classify and understand them. When Charles Doolittle Walcott collected his tens of thousands of Burgess Shale specimens in the early 20th century, he was confronted with an impossible task. He had before him a fossil assemblage that represented an ecosystem unlike any in the modern world, populated by animals that defied easy classification. Many of these animals had body plans that do not correspond to any living phylum. They had structures, appendages, mouthparts, sensory organs, for which there are no modern analogues. They were, in the most literal sense, incomprehensible to a scientist working within the taxonomic framework of the early 20th century. Walcott's response to this challenge was to force the Cambrian animals into existing categories. He classified them as primitive versions of modern groups, early crustaceans, early worms, early jellyfish, even when the fit was poor. This approach, which the paleontologist Stephen Jay Gould later criticized in his influential book, Wonderful Life, was not unreasonable given the state of knowledge at the time. Walcott was working within a framework that assumed all animals must belong to known groups. The idea that the Cambrian might contain animals belonging to entirely new, now extinct body plans was not part of his conceptual vocabulary. The re-examination of the Burgess Shale fauna in the 1970s and 80s, led by Harry Whittington, Derek Briggs, and Simon Conway Morris at Cambridge University, shattered this framework. These researchers showed that many of Walcott's identifications were wrong, often spectacularly so, and that the Cambrian fauna included animals that could not be assigned to any modern group. These weird wonders, as Gould called them, represented evolutionary experiments that had no descendants in the modern world. They were dead ends, branches of the tree of life that had been pruned by extinction, leaving no living representatives. Anomalocaris was perhaps the most spectacular of these weird wonders. Its three-part misidentification, the arm as a shrimp, the mouth as a jellyfish, the body as a sea cucumber, was a direct consequence of the shoehorning approach. Each body part, taken in isolation, could be forced into an existing category. But when the parts were assembled into a whole, the result was an animal that fit no known category at all. It was something entirely new. The recognition of Anomalocaris as a single, unified organism was more than just the correction of a taxonomic error. It was a conceptual breakthrough that forced scientists to rethink their assumptions about Cambrian life. If a single animal could be so strange that its body parts were misidentified as three separate organisms from three different phyla, then what else in the Cambrian might be misunderstood? What other fossils, sitting in museum drawers, classified as mundane members of modern groups, might actually be fragments of extraordinary, unprecedented animals? This question has driven Cambrian paleontology for the past 40 years, and the answers have been consistently surprising. The Cambrian fauna includes animals like Opabinia, a five-eyed predator with a forward-facing nozzle that looked like nothing else on Earth. It includes Hallucigenia, an animal so strange that its original reconstruction had it upside down and backwards. What was initially interpreted as a row of stilt-like legs turned out to be protective spines on its back, and what was thought to be a row of tentacles on its back turned out to be its actual legs. It includes Wiwaxia, an oval-shaped, scale-covered creature whose affinities are still debated. And it includes many, many others, an entire menagerie of evolutionary experiments, each one challenging our assumptions about what an animal can look like and how it can live. The Cambrian is, in many ways, the ultimate test of paleontological imagination. It is a period so remote, so different from the modern world, that our usual reference points fail us completely. The animals do not look like fish or amphibians or reptiles or mammals. They do not look like insects or spiders or crabs. They do not look like worms or snails or starfish. They look like themselves, unique, unprecedented, and until we learn to see them clearly, incomprehensible. The story of Anomalocaris and its misidentification is not just a tale of scientific error. It is a tale of the limits of human perception. We see what we expect to see. We categorize the world according to the frameworks we have been taught. And when the world presents us with something that does not fit those frameworks, we either ignore it, distort it to make it fit, or, in the best case, we expand our frameworks to accommodate it. The expansion of our frameworks to accommodate the weirdness of the Cambrian has been one of the great intellectual achievements of modern paleontology. It has required not just better fossils and better analytical tools, but a fundamental shift in the way we think about the history of life. We have had to accept that the past was not simply a less developed version of the present. It was genuinely different in ways that challenge our most basic assumptions about what life is and what it can be. This is a lesson that extends far beyond paleontology. In every field of human endeavor, there is a tendency to interpret the new in terms of the old, to force unfamiliar phenomena into familiar categories. This tendency is useful. It allows us to navigate a complex world without being overwhelmed by novelty. But it can also blind us to the genuinely unprecedented. The Anomalocaris story is a reminder that the world is often stranger than we think, and that the most important discoveries are sometimes the ones that force us to see what we have been trained not to see. Now let us return to the desert and to Dinosaurs, the wonderful terrible hand that puzzled scientists for 50 years. In Part 1, we told the story of the discovery, the speculation, and the eventual revelation. But there is more to explore here, specifically, the role of fossil poaching in perpetuating the mystery, and what the eventual resolution tells us about the power and the limitations of prediction in paleontology. The Dinosaurs mystery lasted from 1970 to 2014, 44 years, during which the animal was known only from its enormous arms. During that time, the arms became one of the most famous unsolved puzzles in paleontology. They were displayed in museums, featured in documentaries, and discussed in countless scientific papers. They were, in a sense, celebrities, fossils that had transcended their scientific significance to become cultural icons. But behind the glamour of the mystery lay a darker story. As we mentioned in Part 1, the original Dinosaurus quarry was looted by fossil poachers at some point after the initial excavation. Significant portions of what may have been a more complete skeleton were illegally removed and sold on the black market. Some of this material eventually surfaced in private collections and was identified as belonging to Dinosaurus, but by then, the damage was done. The specimens had been removed from their geological context, destroying crucial information about the stratigraphy, taphonomy, and associated fauna of the site. And the delay in recovering this material added years or even decades to the mystery. Fossil poaching is not a minor problem. It is a systematic, ongoing, and deeply damaging assault on the scientific record of life on Earth. The international trade in illegally collected fossils is worth millions of dollars annually, driven by the demand from private collectors, decorators, and in some cases, even museums that are willing to look the other way when it comes to the provenance of their specimens. The consequences of this trade are devastating. Every fossil that is illegally removed from a site is a piece of evidence that is permanently compromised. A fossil without context, without information about where it was found, what layer it came from, what other fossils were associated with it, is like a sentence torn from a book. It may still be interesting, but it has lost much of its meaning. The geological context of a fossil is often as important as the fossil itself, because it tells us about the age, environment, and ecological community of the animal that left the remains. In the case of Dinosaurus, the poaching did more than delay the resolution of the mystery. It also created a gap in the scientific record that can never be fully closed. The material that was illegally removed from the quarry was eventually recovered and incorporated into the 2014 description, but the contextual information, the position of the bones in the rock, their relationship to other fossils in the quarry, the details of the sedimentology, was lost forever. This information might have provided additional insights into the animal's behavior, ecology, and environment. We will never know. The Dinosaurus case is a cautionary tale about the real costs of the illegal fossil trade. It is a reminder that fossils are not just pretty objects to be bought and sold. They are scientific data, irreplaceable, irreproducible data about the history of life on Earth. When they are removed from their context, when they are traded on the black market, when they end up in private collections where they are unavailable for scientific study, a piece of the story of life is lost. And unlike most losses, this one is permanent. You cannot go back and re-excavate a looted quarry. You cannot reconstruct the contextual information that was destroyed by careless or illegal collection. What is lost forever. But let us also consider the other side of the Dinosaurus story, the eventual revelation of the animal's true nature, and what it tells us about prediction in paleontology. For 50 years, scientists tried to predict what Dinosaurus looked like based on its arms alone. They produced a wide range of hypotheses, from giant carnivore to giant sloth to giant anteater. None of these predictions was correct. The real Dinosaurus, a giant, humpbacked, duck-billed ornithomimosaur, was not predicted by anyone. This is not because the scientists who speculated about Dinosaurus were incompetent. It is because the task they were attempting, predicting the overall appearance of an animal from a single body region, is fundamentally impossible when the animal in question does not conform to the known patterns of its group. Prediction in paleontology relies on pattern recognition. If you know the general proportions and anatomy of theropod dinosaurs, you can often make reasonable predictions about the overall appearance of a new theropod based on a limited amount of material. If you find a partial skull that looks like a tyrannosaur skull, you can predict, with reasonable confidence, that the animal had short arms, powerful legs, and a large body. If you find a claw that looks like a dromaeosaur claw, you can predict, with reasonable confidence, that the animal had a stiffened tail, grasping hands, and a relatively lightweight build. But these predictions only work when the new animal conforms to the established patterns of its group. When the new animal is an outlier, when it represents a departure from the typical body plan of its family, prediction breaks down. And Dinosaurus was a profound outlier. It was an ornithomimosaur, but it looked nothing like any other ornithomimosaur. Its proportions, its skull shape, its vertebral sail, all of these features were unique, unprecedented, and unpredictable from the arms alone. The arms themselves, ironically, were one of the least informative parts of the animal. They were large, yes, and powerful. But large, powerful arms are found in many different groups of theropods, and they can serve many different functions. The arms alone did not point clearly toward any one type of animal. They were consistent with a carnivore, an omnivore, a herbivore, a tree climber, a digger, or a swimmer. Without the rest of the skeleton, the arms were ambiguous, a Rorschach test, just like the Megarachne fossil. The lesson of Dinosaurus is that prediction has limits, and those limits are defined by the diversity and unpredictability of evolution. We can predict what a typical member of a group looks like, but we cannot predict the outliers, the oddballs, the evolutionary experiments that break the rules. And in paleontology, the outliers are often the most interesting animals, the ones that challenge our assumptions and force us to expand our understanding of what is possible. Dinosaurus was such an outlier. It was a dinosaur that nobody predicted, nobody imagined, and nobody would have believed if they had seen it on a movie screen. It was too strange for fiction. And that, in the end, is what makes it so magnificent. Not because it confirmed our expectations, but because it shattered them. Not because it fit the pattern, but because it created a new one. And now we come to the final chapter of our story, the coelacanth, the living fossil, the fish that refused to die. In part 1, we told the basic story of the coelacanth's discovery and its significance. But there is much more to explore, because the coelacanth case raises questions that go to the very heart of what we think we know about the history of life on Earth. Let us begin with the concept of the living fossil itself. The term was coined by Charles Darwin, who used it to describe organisms that appeared to have changed very little over long periods of evolutionary time. The coelacanth is often cited as the quintessential living fossil, and it is true that its basic body plan has remained remarkably consistent over hundreds of millions of years. A modern Latimeria looks, superficially, very similar to its Cretaceous ancestors. The same lobed fins. The same thick scales. The same distinctive tail shape. The overall architecture of the animal appears to have been conserved to a remarkable degree. But the concept of the living fossil is misleading, and it is important to understand why. No living organism is a fossil. No living organism is unchanged. Every species alive today is the product of an unbroken chain of evolution stretching back to the origin of life. Even species that appear superficially similar to their ancestors have undergone significant genetic and physiological changes over millions of years of evolution. The coelacanth of today is not the coelacanth of the Cretaceous. It is a modern animal, with a modern genome, adapted to modern environmental conditions. The concept of the living fossil implies stasis, the idea that some organisms have essentially stopped evolving, frozen in an ancient form while the rest of life races ahead. This is biologically impossible. Evolution does not stop. Every generation of every species is subject to natural selection, genetic drift, mutation, and other evolutionary forces. These forces may produce visible changes in some lineages and relatively subtle changes in others, but they are always at work. The difference between a living fossil and a rapidly evolving species is not a difference in the rate of evolution. It is a difference in the rate of morphological change, the rate at which the visible appearance of the animal changes. Some lineages evolve rapidly in ways that are easy to see, changes in body size, limb proportions, skull shape, tooth morphology. Other lineages evolve just as rapidly but in ways that are less visible, changes in physiology, biochemistry, behavior, and genetic regulation. The coelacanth may look much like its Cretaceous ancestors, but its immune system, its metabolic pathways, its reproductive biology, and its genetic makeup have all been shaped by 66 million years of natural selection. So when we call the coelacanth a living fossil, we are using a metaphor, not stating a biological fact. The metaphor captures something true, the remarkable morphological conservatism of the coelacanth lineage, but it obscures something equally important, the fact that the living coelacanth is a modern animal, as fully evolved and as exquisitely adapted to its environment as any other species on Earth. Understanding this distinction is important because it colors how we think about the coelacanth's survival. If we believe the coelacanth is a genuine relic of the past, unchanged for millions of years, then its survival seems miraculous, a freak of nature, an improbable exception to the normal rules of evolution and extinction. But if we understand the coelacanth as a modern animal that happens to resemble its ancestors in certain visible ways, then its survival becomes less mysterious. It survived because it was adapted to its environment. It survived because natural selection continued to act on its lineage, maintaining the features that worked and modifying the ones that did not. It survived because, in the deep waters of the western Indian Ocean, being a coelacanth was a perfectly viable way to make a living. The coelacanth's survival also tells us something important about the nature of mass extinctions. The end Cretaceous extinction, which occurred approximately 66 million years ago, is one of the 5 great mass extinctions in the history of life. It wiped out roughly 75% of all species on Earth, including all non-avian dinosaurs, all pterosaurs, all large marine reptiles, and many groups of fish, invertebrates, and plants. The cause was the impact of a massive asteroid in what is now the Yucatan Peninsula, which triggered a global environmental catastrophe, wildfires, tsunamis, a prolonged impact winter, caused by dust and debris in the atmosphere, and a collapse of photosynthesis-based food chains. The coelacanth survived this catastrophe. How? The answer lies, at least in part, in its ecology. Modern coelacanth are deep-water animals that live along steep, rocky submarine slopes at depths of 100 to 700 meters. They are slow-moving, low-energy animals with very low metabolic rates. They feed on fish and squid, and they are probably not dependent on photosynthesis-based food chains in the way that many shallow-water organisms are. This ecological profile may have helped them survive the end Cretaceous crisis. While the surface waters were ravaged by the effects of the asteroid impact, light blocked by atmospheric debris, temperatures plunging, photosynthesis shutting down, the deep waters may have been relatively buffered from the worst effects. The coelacanth, living in the deep and feeding on prey that did not depend on surface productivity, may have been insulated from the catastrophe that destroyed so many other groups. This is speculative, of course. We cannot know for certain why the coelacanth survived and so many other groups did not. But the hypothesis is consistent with what we know about the ecology of the living animal and the environmental effects of the end Cretaceous extinction. It suggests that survival was not random, but was mediated by ecological factors, that the animals most likely to survive a mass extinction are those whose lifestyles are least dependent on the environmental conditions most disrupted by the extinction event. This insight has implications far beyond the coelacanth. It suggests that mass extinctions are not equal opportunity killers. They do not wipe out species at random. They impose selective pressures that favor certain ecological strategies over others. Understanding which strategies are favored, which traits make species more or less vulnerable to extinction, is one of the most important questions in modern paleontology and conservation biology. The coelacanth story also raises the question of what else might be out there, waiting to be discovered. If a large, conspicuous fish can survive undetected for 66 million years, what about smaller, less conspicuous organisms? The fossil record is full of groups that disappear at various points in geological time, and it is tempting to assume that they are all truly extinct. But the coelacanth reminds us that absence from the fossil record is not proof of absence from the planet. Some of these, extinct, groups may still exist, hidden in unexplored habitats, awaiting discovery. This is not idle speculation. In the decades since the coelacanth was rediscovered, several other organisms have been found alive that were previously thought to be extinct. The dawn redwood tree, Metasequoia, was known only from Cretaceous and Tertiary fossils when a living population was discovered in a remote valley in China in 1944. The woolly pine, Willemia nobilis, was known only from Jurassic fossils when living trees were found in a remote canyon in Australia in 1994. And in the deep sea, new species are being discovered regularly that belong to groups thought to have vanished millions of years ago. The lesson is clear: the fossil record is not a complete inventory of life on Earth. It is a partial, biased, and often misleading sample. It is an extraordinary resource, the only direct evidence we have of the history of life, but it must be interpreted with caution and humility. The coelacanth is a permanent reminder of this humility, a living rebuke to anyone who claims that we know everything there is to know about the history of life on Earth. We do not. We never will. And that is what makes the quest so endlessly fascinating. Let us also consider the human dimension of the coelacanth story, because it is one of the most compelling aspects of the entire affair. The discovery of Latimeria columnae was not the work of a single brilliant scientist making a breakthrough in a laboratory. It was the result of a chain of events involving a fisherman, a museum curator, and a chemistry professor, an improbable trio of characters who, through a combination of skill, persistence, and extraordinary good fortune, produced one of the most important zoological discoveries of the 20th century. Hendrik Goosen, the fisherman who caught the coelacanth, did not know what he had. He was a practical man, interested in his catch primarily as a source of income. But he had the presence of mind to set aside the unusual fish and to notify Marjorie Courtney Latimer, the museum curator, about his find. Without Goosen's attentiveness, the coelacanth might have been gutted, cleaned, and sold for food, and the discovery might never have been made. Courtney Latimer, for her part, displayed remarkable intuition and determination. She was not a fish specialist. She had no particular expertise in coelacanth or lobe-finned fish. But she recognized, instinctively, that the fish was something extraordinary. And she fought to preserve it, battling the South African summer heat, the lack of adequate preservation facilities, and the skepticism of colleagues who could not understand why she was making such a fuss about a single fish. Without Courtney Latimer's determination, the specimen might have been lost before anyone with the expertise to identify it could examine it. And J.L.B. Smith, the chemistry professor who served as the identifier, brought the crucial expertise that the other two lacked. Smith was an amateur ichthyologist, but he was a gifted and dedicated one, with an encyclopedic knowledge of fish anatomy. When he saw the sketch and description that Courtney Latimer sent him, he recognized the coelacanth immediately. His reaction, the shock, the disbelief, the electrifying realization that a living fossil had been pulled from the sea, has become one of the legendary moments in the history of science. But Smith's role did not end with the identification of the first specimen. He was obsessed with finding a second one. He understood that a single specimen, however remarkable, would be vulnerable to skepticism and criticism. He needed more. He needed proof. And so he launched a campaign that consumed the next 14 years of his life, distributing leaflets along the East African coast, offering a reward for a second coelacanth, and traveling tirelessly to follow up on every possible lead. The second coelacanth was finally caught in 1952, off the Comoro Islands between Madagascar and the east coast of Africa. Smith flew to the islands in a military aircraft lent to him by the South African government, arriving in time to examine the specimen in a state of high emotion. By all accounts, he wept when he saw the fish. 14 years of searching, 14 years of doubt and frustration and obsessive dedication, had finally been vindicated. The discovery of the second coelacanth confirmed that the first was not a fluke. Coelacanth were not just surviving, they were maintaining a population, reproducing, carrying on the business of life in the deep waters of the western Indian Ocean. They had been doing this for 66 million years, since before the fall of the dinosaurs, since before the rise of the mammals, since before the emergence of human beings. They were, in a very real sense, older than history. The coelacanth story is a story about the limits of knowledge. It is a story about the assumptions we make when we interpret the fossil record and the dangers of treating those assumptions as certainties. But it is also a story about the power of observation, the importance of curiosity, and the value of persistence. Goosen, Courtney Latimer, and Smith were not paleontologists. They were ordinary people, a fisherman, a curator, and a chemistry teacher, who happened to be in the right place at the right time and who had the wisdom and the determination to recognize and preserve an extraordinary discovery. This is a reminder that science is not just the province of professionals. It is a human enterprise open to anyone with eyes to see and the curiosity to ask, "What is this?" Some of the most important discoveries in the history of science have been made by amateurs, by outsiders, by people who were looking for one thing and found something else entirely. The coelacanth was found by a fisherman. The Burgess Shale was found by a geologist looking for something else. The first dinosaur bones were found by quarry workers, farmers, and collectors who had no idea what they were looking at. These discoveries remind us that the natural world is full of surprises, and that those surprises are available to anyone who pays attention. You do not need a degree in paleontology to find a fossil. You do not need a laboratory to make an observation. You need only the willingness to look, the courage to question, and the honesty to admit when what you see does not match what you expected. As we come to the close of this exploration, let us step back and consider the larger picture. We have examined 6 cases of paleontological misidentification, each one unique in its details but connected by common themes. What do these stories, taken together, tell us about the nature of scientific knowledge? First, they tell us that science is self-correcting. Every mistake we have discussed was eventually identified and corrected. Some corrections took years, others decades, and one, the Anomalocaris misidentification, took nearly a century. But in every case, the error was detected, the evidence was re-examined, and the truth, or at least a closer approximation of the truth, emerged. This self-correcting capacity is not a weakness of science. It is its greatest strength. A system of knowledge that cannot correct its own errors is not a system of knowledge at all. It is a dogma. Science, by contrast, is built on the assumption that current knowledge is provisional, that all hypotheses are subject to revision in light of new evidence, and that the goal is not to be right but to be less wrong. Second, they tell us that the difficulty of a scientific problem is often inversely proportional to the amount of evidence available. The cases we have examined, Megalosaurus, Megarachne, Therizinosaurus, Pterodactylus, Anomalocaris, Dinosaurs, are all cases in which the available evidence was limited, fragmentary, or ambiguous. In each case, the misidentification arose because the scientists involved were forced to make inferences from inadequate data. The lesson is obvious but bears repeating: the less evidence you have, the more likely you are to be wrong. And in paleontology, limited evidence is the norm, not the exception. Third, they tell us that conceptual frameworks matter as much as raw data. The same fossil can lead to radically different interpretations depending on the conceptual framework of the interpreter. Collini saw an aquatic animal in the Pterodactylus fossil because his framework did not include the concept of a flying reptile. Maleev saw a turtle in the Therizinosaurus claws because his framework did not include the concept of a herbivorous theropod. Walcott saw 3 separate organisms in the Anomalocaris fossils because his framework insisted that all animals must belong to known groups. In each case, the data were the same. What differed was the lens through which the data were viewed. This has implications that extend far beyond paleontology. In every field of human inquiry, we interpret evidence through the lens of our pre-existing beliefs, assumptions, and conceptual categories. These lenses are necessary. Without them, we would be overwhelmed by the raw complexity of the world, but they are also limiting. They filter out information that does not fit. They highlight information that confirms what we already believe. They make us see patterns that may not be there and miss patterns that are. The only defense against the distorting effects of our conceptual lenses is awareness. If we know that our frameworks can mislead us, we can take steps to guard against it. We can seek out alternative interpretations. We can invite criticism from colleagues who work within different frameworks. We can cultivate the habit of asking, what would this evidence look like if my framework is wrong? These are not natural habits. They require deliberate effort and intellectual discipline. But they are essential for the progress of any field that aims to understand the truth about the natural world. Fourth, these stories tell us that collaboration is essential. Every correction we have discussed was the result of collaboration between researchers from different institutions, different countries, different disciplines, and different generations. The re-examination of the Burgess Shale required a team of researchers with expertise in invertebrate anatomy, functional morphology, and evolutionary biology. The reclassification of Megarachne required specialists in both arachnid and eurypterid anatomy. The resolution of the Dinosaurs mystery required an international team with access to material from Mongolia, South Korea, and the black market. And the discovery of the coelacanth required the combined efforts of a fisherman, a curator, and an ichthyologist. Science is often portrayed as the work of lone geniuses, solitary figures having eureka moments in their laboratories. This image is misleading. In reality, science is a deeply social enterprise. It depends on the exchange of ideas, the sharing of data, the critical evaluation of hypotheses by a community of peers. No individual scientist, no matter how brilliant, can see the whole picture. Each researcher contributes a piece of the puzzle, and it is only when the pieces are assembled by the community that the full picture emerges. This is particularly true in paleontology, where the evidence is scattered across the globe, housed in thousands of institutions, and studied by researchers who speak different languages, use different methods, and approach the material from different theoretical perspectives. The integration of this dispersed and diverse body of knowledge is one of the great challenges of the field, and it is a challenge that can only be met through collaboration, communication, and a shared commitment to the pursuit of truth. Fifth and finally, these stories tell us something about the nature of truth itself. In paleontology, as in all of science, truth is not a fixed point that you arrive at and stay at forever. It is a moving target, a horizon that recedes as you approach it. Every answer raises new questions. Every discovery reveals new mysteries. Every correction of an old error opens the door to new errors that will, in turn, need to be corrected. This can seem discouraging. If we can never arrive at the final, definitive truth about the past, what is the point of trying? The answer is that the value of science lies not in the destination, but in the journey. The process of inquiry, of asking questions, gathering evidence, forming hypotheses, testing them, revising them, and asking new questions, is itself the point. It is through this process that we deepen our understanding of the natural world, expand the boundaries of what we know, and push back the darkness of ignorance. The past is vast, deep, and largely inaccessible. We will never know everything about it. We will never reconstruct every extinct animal with perfect accuracy. We will never fill every gap in the fossil record. But we can, and do, make progress. We can, and do, get closer to the truth with each new discovery, each new analysis, each new generation of researchers. And the mistakes we make along the way are not obstacles to progress. They are the substance of progress. They are the raw material from which better understanding is forged. Let us close with a thought experiment. Imagine a paleontologist 200 years from now, looking back at our current understanding of prehistoric life. What will she think? Will she marvel at our accuracy? Or will she shake her head at our errors, just as we shake our heads at Buckland's lizard-like Megalosaurus and Maleev's turtle-shaped Therizinosaurus? The answer, almost certainly, is both. She will admire the progress we have made, the tools we have developed, the frameworks we have built. And she will also see errors that we cannot see, blind spots that are invisible to us because they are built into the very foundations of our current understanding. She will know things about the past that we do not yet know, and she will wonder how we missed them. This is the nature of science. It is a process without an endpoint, a journey without a destination. Every generation stands on the shoulders of the previous one and sees a little farther. Every generation also discovers that the view from higher up reveals new complexities, new puzzles, new reasons for humility. The animals we have discussed in this documentary, Megalosaurus, Megarachne, Therizinosaurus, Pterodactylus, Anomalocaris, Dinosaurs, and the coelacanth, are all, in their different ways, monuments to this process. They are monuments to the courage of the scientists who first described them, the persistence of the researchers who corrected the errors, and the inexhaustible creativity of the natural world that produced them. They are also monuments to the power of curiosity. Every one of these stories began with someone finding a strange object in the rock and asking, "What is this?" That simple question, "What is this?" is the engine of all science. It is the question that drives us to dig, to study, to debate, to revise, to dig again. It is the question that transforms a fragment of ancient bone into a window onto a vanished world. And it is the question that will continue to drive paleontology forward, into the next century and the next millennium and beyond, as long as there are people with the curiosity to ask it and the courage to accept that the answer may be different from what they expected. The past is not dead. It is still speaking to us, through the bones and shells and impressions it has left behind. We are still learning to listen. And the most important lesson we have learned, after 2 centuries of trying, is this: we do not yet know how to listen well enough. We are getting better. We are always getting better. But we are not there yet. And that is not a reason for despair. It is a reason for excitement. Because it means that the greatest discoveries are still ahead of us. The most surprising fossils have not yet been found. The most dramatic corrections have not yet been made. The most astonishing animals are still waiting in the rock, waiting for someone to dig them out and ask the question that will unlock their secrets. What is this? We do not know yet. But we will keep asking. The rocks are patient. They have been waiting for hundreds of millions of years. They can wait a little longer. And when we finally find the answers, when we finally see the full picture, or as close to the full picture as we will ever get, we will look back at the errors of the past not with embarrassment but with gratitude. Because every error was a teacher. Every mistake was a stepping stone. Every wrong turn was a lesson in humility, a reminder that the natural world is vaster, more complex, and more wonderful than our small human minds can easily comprehend. That is the ultimate lesson of the greatest mistakes in paleontology. Not that science fails, but that science learns from its failures. Not that scientists are fallible, but that their fallibility is the source of their strength. Not that the past is unknowable, but that the effort to know it, the long, difficult, error-strewn, magnificent effort, is one of the noblest undertakings of which our species is capable. The bones in the rock are speaking. They have always been speaking. And we, slowly, imperfectly, but with ever-increasing clarity, are learning to hear what they say. What is this? It is the question that started everything. And it is the question that will carry us forward, into the deep time that lies ahead, for as long as there are minds curious enough to ask it, and hearts brave enough to accept the answer, whatever it turns out to be. Thank you for watching. If you enjoyed this documentary, please subscribe to the channel for future videos. Leave a comment below telling us where you are watching from and what time you are watching. Your support helps us continue creating content that explores the greatest stories ever told, the stories written in stone, waiting to be read.